The rest of the class starts today. You could think of what we did so far as sort of a mini class that kind of skimmed the surface of thermodynamics without really going terribly deep. The remainder of the class, the last 2/3, all builds on itself. It starts with the principles we do today. It's all electricity and magnetism. And when we get to the last day of class, we'll sort of have, I don't know, it's like all of the equations will come together and we'll reach this pinnacle and we'll be like, look at that. Look at what we learned over 2/3 of the semester, and it'll all come together in one lecture, all right? So as we proceed today, we're going to start with what I would call some really sort of basic ideas. Ideas that you might be like, oh, this is boring, and I played with some of this when I was in 8th grade or something, all right? I need to get everybody on the same foundation, first of all. So you could think of the first, 6, 7, 8 slides here as sort of fundamentals, just to make sure that we're on the same page and you kind of understand where we're starting from. And at that point, we'll finally hit sort of the first main law of electricity and magnetism, and we'll start to build from there forward, okay? So are you excited?
Yeah.
Why is there a delay? It's like, are you excited? Yeah. Is the speed of sound that slow in this room or something? I don't think so. Are you excited? That was a little faster, although not all convincing. There was a lot, yeah. Okay, fine. We're all going to fake. It'll be fine. So it all starts today with the principle of what we call electric charge. The principle of electric charge, which is a property that some elementary particles have, okay? If you wanted to dig a little deeper into but what is it exactly? Nah, that's beyond this class, raises a lot of fundamental questions, is active research, and also it's a similar question what is mass really? We understand it, we can use it, we understand how it behaves, but when you really get down to the nitty-gritty of but what is it? Why is this a thing that I can touch? Those are deep fundamental questions that we're not going to go there, all right? So electric charge all starts with the idea that the elementary charge, which you can see the value there, and also the symbol, little e, exists on the proton and the electron. It just happens to be negative in the case of the electron, positive in the case of the proton. And if you're thinking, well, what's positive and what's negative? Well, not really anything. As we'll see a little bit later, it's kind of a completely made up. It's just there seems to be two types of charge that behave differently. Let's just call one of them positive and one of them negative. There's nothing inherently positive or negative about either one of them, okay? So we are going to say that, atoms have sort of a basic rough structure like this. I think most of us understand that this is sort of an elementary model. It doesn't really look like a little solar system, if we really get down to it, but it's good enough for our purposes. And when it comes down to it, also, the nucleus is going to be positively charged because there will be some combination of protons and neutrons in there, and it's surrounded by some cloud of negatively charged electrons. So most objects, have an equal number of these things. So just like in the diagram we have there, I see 3 negatives and 3 positives. We would say that object and that atom is neutral. There's an equal number of both of those. So we could scale that all the way up and just sort of pretend that if we could go through this entire table at the front, which that is a large table. That's a lot of table, all right? There's a lot of atoms that are in there. If we could somehow go through and count every electron and every proton, if we're going to say that this thing is not charged, there should be an exact equal number of those, at least roughly, okay? An exact equal number. We're often going to be dealing with things where it's it's up an electron or down an electron. It's kind of a little bit charged. We're not going to deal with things that are a lot charged. So if something is not neutral, if something is going to possess electric charge, either I have to have an electron or proton all by itself, or a group of electrons or protons all by itself, or in the case of a piece of matter, I have to have either an excess or a deficit of electrons. For good reasons, the protons, the positive charges that are in the nucleus, they're sort of stuck, right? If you try to, say, excise a proton from a nucleus, Bad things occur, all right? So we're going to assume that for our principles, like the positive charges, they're in place. They're in the matter. They're stuck. They're not going to leave. But the electrons, on the other hand, are relatively loosely bound, especially compared to how strongly the protons are bound in the nucleus, such that it's relatively easy for me to say, take an electron off of an object, or take 10 electrons off of an object, or take 50 electrons off of an object. And if that's the case, well, it doesn't have enough electrons to balance out the positive charge. We would say that that object is positively charged because of missing electrons, all right? The other option would be like, hey, I've got some extra electrons. Object, why don't you take it? And all of a sudden, it's possible maybe for a bulk object to have a few extra electrons, in which case now there's too many electrons to cancel out the protons, and we have an object that's net negatively charged, okay? Fundamentally, that's what's happening. But we're going to kind of tuck it in the back of our mind for most of the semester. Like, we can always kind of go back to that and say, they told me this object is charged. Like, there's a lot I can do with that from solving problems and stuff. And often we won't have to go back and be like, okay, that means it has 3 extra electrons. Like, we don't really need to think about that most of the time. But that idea might help if you get a little confused in the theory and, like, the expansiveness of the equations. And you're like, what are we talking about again? It all goes back to this, okay? Either a deficit or an excess of electrons. So we can also say that because it's based on this elementary charge, the amount of charge that exists on a proton or an electron, well, we're not going to divide that down any further. If something is charged, the amount of charge on that object has to be an integer multiple of the elementary charge. It's because I took off a whole electron or added a whole electron. I can't like put on 2/5 of an extra electron. That doesn't make any sense, okay? It's all in integer multiples of E. Good so far? Pretty basic, pretty obvious perhaps. Yeah, you feel good. Is the food good? Yeah, Chipotle? Yeah, Chipotle. I had to quit Chipotle. No? Who's off of Chipotle? Who loves Chipotle? Who doesn't care at all? I'm sorry, we're voting on your food now. That's just what's happening. I don't know. I'm a germaphobe overall. And when it's like, when things were happening with Chipotle a couple of years ago, people were getting sick, especially when it was at the Chipotle right down the street that I'd been to many times. I was just like, I don't know, that food just didn't look as good anymore. I think I'm going to stay away. So I haven't been back. And I don't think I can. But it's really good though, isn't it? Yeah. You're fine. Don't worry about it. Your food's good. I just couldn't take it anymore. So I'm going to turn my back and just ignore your food back there. So, elementary charge. You can see, first of all, we have hinted at the unit we're going to be using. The unit of charge is going to be, as you see down here, the coulomb, which we'll represent with just a C. And also, we will use one of 2 symbols to represent charge. Why does Q represent charge? Who knows? Probably because C was used by the unit. All right, that would just get confusing otherwise. Sometimes we'll use a big Q, sometimes we'll use a little q. Often we might use big or small just to represent a larger or smaller amount of a charged object, but otherwise they're interchangeable. Which brings me down to this point, which is really going to be the basis of much of what we study in the coming chapters. The idea that we all understand that if I have like charges and I bring them near each other, there is some repulsive force. They want to push each other away. If I have opposite charges, they tend to attract each other, all right? That whole idea clearly indicates that there must be some sort of force that we would call the electric force. And we will deal with it mathematically in a few slides, and it will actually be our first primary principle that we have to deal with. As you'll see, though, in this chapter, and the next chapter, and the next, until we get to magnetism, really all of the concepts that we deal with, however complicated they may be, they're sort of just built on this idea of attraction and repulsion and trying to quantify and understand that and try to figure out how to use it. All right? One last point on this slide is that charge, electric charge, is conserved. The amount of charge that we have is the amount of charge that we have. It can move from one place to another, but we can't create it and we can't destroy it. Whatever you have is what you have. So if some charge is acquired on one object, it had to come from somewhere else. And I should be able to, in my problem, understand, oh, it came from that object over there. It didn't just spontaneously generate itself on the object I'm looking at. All right? Charge is conserved. Next slide, unless anybody wants to stop me. Do you want to stop me?
Of course.
Oh, what are you eating? Ouch. I hope it's good. Huh. Your question.
Yeah, so, like, why didn't they just decide to make it like 1 coulomb per coulomb? Is there any interpretation for the measurement?
It's a good question. I think because of the amount of charge the original studies were likely dealing with, like at that point, things are happening, but we had no idea about electrons and protons, and a unit was established. It just turns out that it's like, oh, we can keep breaking down this farther and farther and farther. A coulomb is actually a lot of charge, an awful lot of charge. I don't have a better reason than that. Anyone else? You're not going to tell me what you're eating, are you? You know I can just walk up there. Do I want one? Ooh, there's multiple of whatever it is. I don't want one. I'm just bothering you, and I'm curious. Looks like quesadillas, yeah? Oh. Huh. Wait a minute. Did you go to Chipotle, too? Don't they have quesadillas at Chipotle? Yeah, I thought so. Because there's a Chipotle eater over here. I feel like someone's handing out Chipotle outside the door, if that's the case. But you didn't go to Chipotle. No. You want me to stop talking to you? A little bit? Okay, yeah. I'll let you eat, though. Did you finish your food over there? Okay, I'll stop talking to you as well. Anybody else eating anything that I can bother? Oh, look at that. Wow, you are not sitting next to a friend, are you? That was faster than, are you excited? That was just, are you eating some? This person is. I'll be up there in a minute. I'm going to keep talking, first of all. So we've got a couple of class questions here that are terribly, terribly basic, all right? So a quick read and then vote with your fingers and we'll move on. Yeah, I don't think you have to think too much. There are these two charged objects. For whatever reason, instead of hanging straight down, they are repelling each other, which means the charges have to be like charges, so they're either both positive or negative. And then I have to apologize for this slide. Something happened in the copy-paste such that there are supposed to be 3 different colors. Do you see 3 different colors? What if we zoom in? If nothing else, it's a fun game, right? There's 2 different colors of blue there. The one on the right is darker? Is that what we think? So we think this is dark blue. I'd agree with that. Which means that all of these in this first column, I think, are dark blue. And then this one is light blue. And you might wonder why I haven't repaired this. Like, I set these slides up a couple years ago. It's just fun for me at this point. Like, why go back and try to fix it? So that one's light blue, and I think the other one is pretty obviously not blue, but who knows? So based on that, what can you conclude about the charges of these objects? Ooh, that means this one over here is light blue. There seems to be a repulsive force happening everywhere between everything, right? So does anyone want to lean toward maybe this one? They all should have the same sign of charge, right? If they're all repelling each other, it's almost a mathematical principle at this point. If A is equal to B and B is equal to C, then A is equal to C. That seems to be kind of what's happening, all right? Yes?
Are those two set up close to each other? Are they in the
Let's pretend there is a hard division there. We're looking at 2 different separate experiments. My apologies for that confusion. Anyone else? Okay. All right, which brings us to material types that we're going to be talking about, just from a rough understanding. I'm wandering back here to check out the quesadillas. Oh, they look good. Yeah, I approve. Yeah, not that you care. And then you're eating something that also looks tasty. Did I just come hungry today, or what? I don't know what happened. Is that from home, or did you buy that somewhere? You made it. Ooh. Yeah, these other people did not make their food. You officially win. That's all there is to it. So 3 different types of materials that we will often refer to, and I'm going to put a hard line right there because that third one really should be in a category all its own, both due to its usefulness, its complexity, and the fact that treating it with any respect really requires way more than whatever time we have in this class. So I'll tell you what it is and just sort of leave it at that point. So first of all, conductors. For example, metals. We will say that in conductors, the electrons are loosely bound and relatively free to move around. And you had sushi. No, you didn't. I thought so. It wasn't good? No? I'm really sorry. Yeah, there's other food. There's at least 3 other places in the room if you want to go get a little more. Yeah. In conductors, we are going to say that the electrons are basically free to move around as long as I give them a reason to. So if for whatever reason a force comes along from other charges and the electrons are, attracted, they're free to go that direction. If they're repelled, they're free to run away, okay? We will treat the electrons as extremely loosely bound and free to move in conductors. Insulators or non-conductors, exactly the opposite. We will say the electrons are tightly bound. So they're basically stuck. If I apply a force from other charges, these electrons are just going to be like, I don't really care. I am where I am. I'm stuck orbiting this atom that I'm orbiting, and that's kind of the end of the story. So, for example, as you might expect, this might be something like rubber or plastic or wood or other such materials. Which brings us to semiconductors. They're sort of in between. And they're in between such that we can fine-tune them to give just a little more conductivity or just a little less conductivity and make them serve our purposes just how we want to. And of course, semiconductors and that whole industry is based in this area. And there's a lot going on there, and I don't want to say anything else because I just won't do it justice, all right? Think of semiconductors as living in between, and we will not do anything with them in this class. So, if I look over to the right, we have some objects that will start to get us familiar with the way we handle charged objects in a physics class. You will notice that they have drawn this first charged object as just being an object that is positively charged, okay? We know if an object is positively charged, the only way I can get it that way is by removing some electrons, okay? However, in a physics class, we're going to kind of pretend things are the other way around. And you're laughing already because you maybe see what's coming, okay? For whatever reason, at least historically, physicists base everything on the idea of the positive charge. So even though we understand now that it's actually electrons that are leaving or coming or departing or being added or subtracted, we're going to pretend that positive charges can move. Yeah, which is fantastic, right? Keep in mind, back in the day, positive charges, it's totally arbitrary. What they decided to call positive and what they decided to call negative was not based on anything at all. They're just like, hey, let's call this thing positive, let's call that thing negative, and off we go. The fact that we call positive charges something that's moving around and treat it that way and pretend it that way, it doesn't affect the mathematics. The math is exactly the same both ways, so we can continue this little fairy tale and everything works, and everything is fine. Just try not to let it stress you out too much, okay? If you need to, and you're just like, I just don't see how positive charges are moving, you can always take diagrams like this and flip them in your head and be like, how can I get the exact same result by thinking about it in terms of electrons, okay? So notice, at the start, we have a charged object, we're going to say is positively charged, and a neutral object, which we understand would have equal positives and negatives throughout it, okay? If I make a connection between them with a piece of metal, a conductor, well, the electrons or any type of charge is basically free to move through the metal because it's a conductor. So you might imagine that Well, all of these charges that are bunched up here, well, they would like to repel each other and get away from each other if I give them a place to go. That's essentially what I do by making a metal connection to the other object, and then things can balance themselves out. Now you can imagine half of the extra charge goes to the other object, such that any repulsive forces are now kind of equal in both directions, and then the system stops. Okay? So if we were to look at the charges that were there, we started with 6 on one, we make the connection, we end up with 3 positive charges on each. If you don't like the positive charges moving around, think about maybe what's actually happening. To get from this state to this state, 3 electrons need to move from here to here, right? At which point I would have a deficit of 3, which gives me a positively charged object, and I would counteract half of these and make it less positively charged, all right? Everyone okay with that? Even if you're not, you have to be, so I'm sorry. Just deal with it. In the figure underneath that, you can see we have the same object where we're making a connection with a non-conductor. Nothing happens. Nothing can flow through the non-conductor because the charges there are bound and not free to move and balance things out. So those repulsive positive charges are still stuck, repelling each other, but they have nowhere to go. And it's kind of sad. Okay? Who's got questions or thoughts? Anything? Anybody? You're perfectly happy? Are any of you hungrier now than when you entered the room? A few of you, yeah. You even had sushi. It was that bad. You ate it and it made you hungrier. Wow, that's pretty serious. That is some bad food. Man, should we all know where you got it so we don't go there? Noted. Noted. Which brings us to this odd-looking diagram all the way around. Like fur. It just says fur. It's like someone sadly went up to an animal and just scraped a little fur off, and then now there it is. It's kind of disgusting, but I got it out of a textbook, and you can even see which textbook right down there in the corner. Physics by some guy named Walker, 4th edition. There you go. All right, so I don't know what's up with that. So we're going to look at 3 different ways we can charge objects. In other words, give them a net positive or negative. The first one of these is of really no practical value to us. I only give it to you for historical interest, all right? You can imagine centuries ago, people really had no idea what was going on at a microscopic level, right? But things maybe happened by accident sometimes, and maybe one piece of material would brush up against another piece of material, and the next thing you know, something sparks when it comes into contact with something else. So if you lived back in that day, perhaps you would be one of the enterprising types that's I don't know what's going on here, but I need to know more. So what did you do but find every type of material you can and just start rubbing them together, right? And just be well, I rubbed these together, nothing happened. I rubbed these together, nothing happened. And you can imagine a huge journal of just trying to figure all this out, okay? Sounds like fun, right? Also sounds a lot easier than being a scientist today. Don't you sometimes feel, I don't know, like halfway a little cheated, and also, thankful that we have all the technology and understanding that we have? Because, back in the day, if you wanted to do science, it's hey, let's rub some things together. That was fun, right? And make a little note. Or it's I wonder what will happen. I know what to do next. Oh. Ooh, and then that's science, and then next thing you know, we understand gravity. Fantastic, right? Now you need, $50 million, state-of-the-art lab, and then maybe you can just scratch the surface a little bit in some area on something new. That kind of makes me sad, doesn't it, you? In a way. Don't you just kind of wish you could just go into your backyard and be hey, here's some things, and then learn something completely new about the universe? That'd be kind of awesome in a way. Also, if I lived back then, thanks to my vision, I would be in a home somewhere because we wouldn't have glasses or contact lenses, and I would not be able to see anything because I can't see this without the contact lenses. So if I were doing the science, it'd be kind of like that, and then nothing would happen. It would be sad, and I wouldn't. they wouldn't let me do science, I don't think, centuries ago, because that would be very sad all around. So I'm glad I live when I live, but it's interesting to think about sometimes. So you'll notice, like here, we've just got this list of various objects that seem to have relative amounts of positive and negative charge when simply physically rubbing those objects against other objects. What's happening is literally removing or adding electrons. Based on how tightly the electrons are bound in a given substance, well, if they're really, really loosely bound, you might imagine that if I physically rub that object against something, I'm actually just scraping electrons off. If they're really loosely bound, like apparently rabbit fur, well, it becomes much more positively charged than something that maybe holds onto its electrons a little better, like silk or paper or, human hair. Yeah, that seems like something that would have been probably one of the first experiments. Like, hey, give me some of your hair. You know, I want to rub that against some, probably not PVC. That don't sound right. But maybe wood or copper or something. You know, that could happen. So you can imagine the ones at the bottom, negative relative charging with rubbing. Well, they tend to hold onto the electrons tighter such that they will scrape electrons off of another object and make themselves relatively negatively charged. So this type of experimentation clearly was done when we didn't know about electrons, didn't know about protons, and simply just looking at these different objects, one could determine, it's like, oh, well, if I rub this object and I rub this object, those two objects attract each other, and then these two objects tend to repel each other. It was determined that something was happening such that there were two different types of charge. That's as much as someone could say at that point in time. There are two different types of charge, and it's basically like, well, let's call the ones that have this type of charge positive. The ones at the top, let's call the ones that have that type of charge negative, and just move on with life. Again, the positive and negative, completely arbitrary, okay? Again, there's no practical benefit to this. So let's move on to the next one where things get a little more beneficial. Your question first. Well, take a look at these objects. There's a lot of non-conductors there. So, yeah, it doesn't really matter. Think about just what we're really talking about is what we would call static electricity when we were younger. You know, rub the heels of your shoe on the carpet. There's no conductors there at all. But still, you can rub off electrons. Yeah. Both involve physical contact, but on the next slide, when we talk about conduction, we're not talking about a physical rubbing or scraping. We're just talking about an instant touch, okay? So in this particular case, yes, this involves physical contact as well, but you'll notice, as in the diagram over here, we just take two objects and do nothing more than a single touch, which can allow a charged object to transfer its charge over to another object, at which point it's like, oh, now I've got a second charged object. I've charged that object through conduction. So perhaps in this case, the charged metal object was charged in some other way to remove some electrons so that when I make a connection physically with another object, it says, I'll take some of your electrons. They're drawn that direction to balance out the charge once again, okay? So the first one, what did we call it here? We just called it physically transfer charge. That's more of a scraping of charge or removing it from one and putting it on the other. Here is just a transfer because I have conductors, I touch them, charges are free to move, okay? This is more like what we saw 2 slides ago when we connected things with a piece of metal, okay? There's nothing else to add to that slide, and yet I have all of this space. What should I do with it? Thoughts? Draw a picture of what? Of food. There we go. Aren't they beautiful? Don't they make you hungry? See, you didn't have me for class last semester. You would have learned quickly that, this is the extent of my artistic ability. So it's like when we had something like a car, has some weight or something, and it's put, it was always just like, okay, I need to draw a car, and then that was the car. And everything is a box with a word in it, no matter what happens. So There you go. I guess I wouldn't even know what to add to that. I guess I could write other little words like, cilantro. What do you mean, what kind of tacos? I generally get an assortment. So, a little chicken, a little pork, a little beef. Yeah, I'm making you hungry now, aren't I? But I like the classic tacos, just onions and cilantro, corn tortillas. I'm sorry, I have to do it again just for myself. There we go. So let's just leave that there. Maybe we'll have a double serving and then move on to the next slide.
Do you draw yourself eating the tacos? Would you draw yourself as a box?
Yeah. There you go. End of story. So, sort of an interjection here before we get to number 3. And I don't want you to take the diagram on the top right too literally, okay? This is not an exact picture of what's happening. I just want to give you an idea of what can happen. Notice the idea here is that charged objects can attract neutral object as well, not just oppositely signed charged object. And this is something that's known as polarization. What happens in polarization is when I bring a charged object near a non-conductor, well, without touching them, you can imagine that even the non-conductor has positives and negatives in it. They're just stuck. But that doesn't mean they don't feel a force. It just means that they feel the force and can't go running over to the other object. So instead, one way to think about this, and yeah, it's not terribly realistic, is just that, well, if I have something positively charged, negatives want to go that way, and they're still going to as much as they're able. So you might imagine the negative charges in the object just being kind of like, it's like they're stuck, and they can't go over there, but they kind of trend that way just a little bit. They've drawn that to an extreme and just pretended that like every atom in there just went, whoop, let's just send all of our negative charges over that way. That's a bit much, okay? Instead, it's just a slight tendency for the negative charge to be a little bit closer to the positive. And because of that, well, there can still be an attractive force that's significant between the conductor and the non-conductor. You've seen this play out when someone takes like little pieces of paper and then charges something like a hair comb and then brings it nearby and it picks up the pieces of paper, right? If the paper was like heavier, you wouldn't have that effect, right? It's a very weak force, and you need something really light to actually see it be attracted and picked up, all right? So just keep in mind that neutral objects can also be attracted to charged objects. Again, I have all this space and nothing else to say about it. Thoughts? There. That's just a little terrifying. Just a little terrifying. Let's make it worse. I fear for the people who didn't come today. They're just going to get the slides, right? And they'll just be flipping through. That'll be fantastic. So what we should do in here somewhere. Gotcha. Yeah, there we go. That'll work. Number 3. What's the point of any of this? I don't know. Number 3 is induction, and this one is the most complicated of the 3 types of ways to charge an object. It also starts to give us a better feel for the way charges behave in objects, okay? So we're going to, first of all, split this right down the middle and take a look at the left 2 cases first of all. So you might imagine if we have a neutral metal rod, first of all, equal numbers of positives and negatives, but the negatives are free to move around if I give them a reason to, okay? So if I bring another charged object nearby, notice these are not touching at all. If they touch, that would be conduction. So here we're just bringing the positively charged object near. Well, if it's near a conductor, well, the electrons are free to go. So what happens, except all the electrons, not all the electrons, that's overstating it, but some of the electrons are like, yay, I see something I'm attracted to, whee, happy Valentine's Day, right? Okay, and they run to the other end of the object. Yeah, I didn't plan that at all. So now we have an object that sort of has a charge separation that's much more dramatic than what we had with the polarization on the previous slide. Now we have a buildup of electrons at one end and a deficit of electrons at the other end. At this point, if we could make some measurements, we would detect that one end of the metal rod is negatively charged and the other one is positively charged, okay? That is the first stage toward charging an object by induction. So what we're going to do now is look at the second case on the right side of the screen, and I apologize for this, but you'll notice that the object that's been brought nearby this time is negatively charged. For whatever reason, these two diagrams are illustrating it backwards. But also it kind of helps a little bit, as we'll see, okay? So we're starting once again with a neutral metal object at the top, so let's write down that this is neutral. And we're making an additional connection this time. This is a symbol that you're going to see over and over and over, and it refers to electrical ground. Electrical ground. We're taking the neutral conducting object and we're connecting it to what's known as electrical ground. Electrical ground is often literally that, the ground. What do I mean by the ground? Earth, terra firma, right? It's like someone's made a connection with a conductor straight into the ground by means of some wire, which would also be a conductor, okay? You can think of electrical ground as the earth, as both a, let's just call it as a reservoir of charge. Meaning it's an extremely large object with lots of electrons. If I have my neutral object and I decide to send a few extra that way, the Earth is like, and that's kind of the end of it, right? It's like something the size of the Earth doesn't care if it gets 3 additional electrons. All of a sudden it's not like balances off in the universe. Or if I have an object that needs a few electrons, the Earth is like, there you go. Like, I don't really care. It's like an infinite source of charge such that I can give up some charge or take some charge at will. And we will often make connections to the Earth in such a way, as we'll see many chapters in the future in circuits. Let me show you how that affects induction, charging by induction. So once again, we're going to do the exact same thing except flip the sign. This time we're going to bring a negatively charged object nearby but not touch the neutral object. Well, what happens is essentially electrons in there are repulsed. They're repelled by the presence of additional electrons. They want to leave, and now I've given them a place to go. Okay? And notice they've even drawn this. Like, let's say these are repulsed, just because it's a fun word. They do not like the presence of additional things like themselves for whatever reason. So off they go into the Earth. And now what happens if I do 2 different things? First of all, I cut this connection so the electrons can't come back. And then I also remove the nearby charged object. The thing that was repelling them into the Earth is now gone, so that, well, they could have come back. They're no longer repelled. But now I've cut the connection so they can't come back. What that means is now I have an object that has lost some electrons. They're gone. They can't come back. They're forever in the Earth. I guess they could come back eventually, but who knows if they're the same electrons? That'd be weird. We should tag them in some way. Are you my electron? Never mind. I'm going to stop talking. So now I have an object that's positively charged. It has a deficit of electrons. Through this process of making some charge go away, not through physical contact, I never touched the charged object to it. I was able to do what we call induce a charge on this object. And now I can take it away, and it's like, yay, now I've got a positively charged object in addition to my negatively charged object. Okay? Any questions or thoughts about induction? Yes. The big difference between polarization and induction is conductor versus non-conductor. So polarization is happening in a non-conductor, sort of a shift in charge, but the object is still neutral the entire time. Here we're actually removing some charge by, again, just bringing an object nearby, and it stays with a deficit of charge, or it has extra charge. The big difference is conductor versus non-conductor. Yes. It's because we're dealing with a conductor here. So if you wanted to think of a conductor kind of like, and this is a rough approximation, as having a series of positive charges that are sort of stuck in place, and then surrounding that is just a sea of negative electrons that can sort of flow wherever you want them to. Okay? That's what happens here when I bring an object nearby that's charged. It'll either push those electrons away to the other end or pull them toward it. But they're actually leaving where they were around their individual molecules. Okay? Who else? Anybody else got any food? You're never going to eat in here again, are you? Or at least half of you. Half of you are kind of like me. I'd be like, once I was singled out, I'd be like, I'm not even coming to class again. But the other half of you are like, I'm going to bring food and see what he says this time. You're weird. Why would you do that? I don't know. So let's take a look at this. Trick question. This is a positively charged rod. Believe it or not, it's labeled as positive. Can you see it? It's there. I keep going in. There's a positive sign there. It just, look, it's very clear on mine. It just doesn't project very well. So this is positively charged. There we go. So what can you say about the sign of this other object? Careful? Yeah, there's the little trick. It could be negative or neutral. Okay, through polarization, that might be possible as well. All right, so let's put a little note here. Polarization. All right, which brings us to some, well, close. Let's do one more of these. Through induction, how do the two different charges end up at the bottom? You can see the two question marks. And once again, I should probably draw in the things you can't see. There's a plus there, and a plus here. They're connected by a conducting wire. And up here, you can't see these either, can you? There's a 0 and a plus and a negative and a plus and a negative and a 0 and a negative and a plus and a plus and a negative. I think most of you are probably there. Okay, we start with two neutral objects. Negatives will be drawn toward that positive, which leaves this net positive behind. When I disconnect the wire, it stays kind of like this. And then, of course, it's going to stay like that because there's no way for the charges to get back where they were. So your answer there is number 3. All right? That is sort of the end of the intro. Does anybody have any questions about any of the intro slides before we jump into the first major topic? Anybody? Anything? Nothing? Are you feeling okay? Maybe we should take a revote at this point. Like analog voting. Let me see where your arms are. Go. Okay. I've seen some that have kind of drifted up from this a little bit. I think that's probably just because you hurt your elbow previously. And now that's just as far as you can go. I don't know. All right? So the first concept is trying to quantify this electric force. We said there's repulsion, there's attraction, depending on whether the charges are like charges or opposite charges. Okay? We can quantify this through what is known as Coulomb's law. Coulomb's law tells us about the electric force. Coulomb's law, let's see, I'm on the electric field. We don't want to do that yet. Let me slide down here. There we go. We're going to start with just the magnitude of this force. So it is a vector, and it is equal to K times the magnitude of one charge times the magnitude of the other charge, divided by the square of the distance between those two charges. K Q1 Q2 over R12 squared, which of course begs the question, what is this thing K? K is approximately equal to 9 times 10 to the 9th. I won't worry about the units because they're not terribly helpful. You can just rearrange the equation and see what the units would be. Oh, I'll write them up there anyway. That's Newton meters squared over Coulomb squared. And this is also related to another constant that's actually a little more helpful, 1 over 4 pi epsilon naught. And this thing is known as the permittivity of free space. Epsilon naught is equal to 8.85 times 10 to the minus 12. And that's Coulomb squared per Newton meter squared. Permittivity of free space. At this point, I just want you to sort of make a note in your brain somewhere, if you can find a little space, and just be like, I remember him introducing the permittivity of free space. And just let it sit there. You're going to use the constant sort of over and over again. It turns out it's going to come back like on the last day of class or like the last couple of days of class in maybe a way that surprises you. I'll leave it at that. Okay? Just keep it in mind. What does it mean? What is the permittivity of free space? Well, I like to look at this word right at the start, permit. Okay? This is sort of how well space itself allows the electric force to pass through it. Okay? Free space is another way of talking about space that essentially has nothing. Think of it as a vacuum. We could write this as the permittivity of a vacuum. Other substances may sort of get in the way of having the electric force propagate through them. So I could have two charges and some material in between that's not a vacuum, and maybe the electric force doesn't get there as well, in which case we would just have an epsilon, not sub naught. We would have an epsilon for that material, the permittivity of that particular material. We'll see that later on. For our purposes, just having air in the room is close enough to free space that we generally won't have to worry about the permittivity of air itself. Okay? Permittivity of free space is generally enough. Also, let's see. Q1 and Q2, there's two charges that have to be involved, so keep in mind this is a Newton's third law. Again, I love the abbreviation. Newton's third law situation. The force that's felt by one charge is also felt by the other charge. They're either both attracted toward each other or they're both repelled by each other. So keep in mind that that applies. If you're worried about the direction of this force, so the direction of the force vector, force electric, it will be along a line connecting the two charges. And we'll add to that according to repulsion or attraction. Along a line connecting the two charges according to repulsion or attraction. So you could look at the diagram in the top right, just draw a line connecting the two charges. Either they have forces that point directly at each other along that line, or they have forces that point directly away from each other, again, along a line that connects the two charges. So we could draw maybe a dotted line there. Coulomb's law. I don't think there's anything terribly strange or confusing about it. We can quantify, calculate, and figure out the exact amount of repulsive or attractive force between charges using Coulomb's law. But you'll notice there at the bottom there are a few different things that we have to point out. This is sort of a simplification. First of all, this is only going to apply for what we call point charges. Charges that we pretend exist at a single solitary point in space and really have no size. This is equivalent to what you might have done last semester in class where, I don't know, maybe you had a large box of some type and maybe it was sliding down an incline, because that sounds like something that happens in Physics 7a, right? And typically, like, you would just sort of ignore the fact that the box maybe had some size and pretend that it actually had an exact position. You might say the box starts at x equals 0. Did it really? Like, well, part of it was at x equals 0, but other parts of it had different positions. You assumed point masses for most of last semester until you started dealing with rotation and things like that, okay? Well, we're doing the same thing here with charges. We're assuming that the charges are not spread out in space, and we can make this assumption as long as they literally are much smaller than R12, the distance that separates them. So if all of a sudden I had two charges that clearly can't exist as a point and are sitting like this and have that finite size and R12 is just this, Coulomb's law is a little bit of an oversimplification for that, okay? They need to be much smaller than the distance that separates them. Also, the charges need to be at rest. If the charges start moving, this all gets much more complicated. We'll deal with moving charges in a few chapters. You could think of everything that we're starting with as a study of electrostatics. We're dealing with charges that are static. They're at rest. Coulomb's law applies if the charges are not moving. Also, if you have more than just the two charges and you're trying to look at the overall net force maybe on another charge, this is a vector. You have to deal with the whole vector addition thing and try to analyze the force that's coming from all of the individual charges. And then one other thing I need to point out is that we are often going to take the idea of charges and relate them back to masses and gravity. One of the hard things that happens in this particular class is that we're dealing with invisible things once again, right? Everything we dealt with thermodynamics, it was like, hey, yeah, this thing has a temperature, but let's pretend that temperature is coming because of all these individual molecules that are flying around in random directions that we can't see. And we made connections between the two that seemed to make logical sense and prove that that microscopic theory made sense. But still, it was a theoretical thing for us. It's something we can't directly observe. That's what's happening throughout electricity and magnetism as well. Charged objects, electrons, protons, things that are missing a couple of electrons. I can't see that. I can't visualize it. I can't look at it. It's hard to imagine. In Physics 7a, it was an awful lot of this, right? Masses. Masses I can understand. This has mass. This has mass. I have mass, right? There's mass all around us. We understand how masses behave. I can take masses, I can throw them through the air, I can apply forces. I can really visualize those things because I can touch them. I can understand those forces. They make sense. For that reason, as much as I can as we go through the concepts, I will take the electricity stuff and try to relate it back to gravity because we understand that force just sort of intuitively. We deal with it every single day. I kind of hate dealing with it, don't you? I've learned, I've only been here, moved here last summer, but I've learned, there's directions on campus you want to walk and directions you don't. At least I don't. Going this direction, all good. Going that direction and then back is all bad. All right? Maybe, you're 20 years old. You don't really care. But eat a few more donuts. And then you'll be in my situation where it's I'm parked that way. Fantastic. I just roll that direction, right? But then it's I'm down there at the car, and it's I need to get to class. It's I don't want to walk that direction. And there's no way around it. We need a skylift or something that goes east-west. You like that? That sounds fantastic. But if you go north-south, all is well. You don't really have to worry about it. Gravity. Gravity, we deal with it all the time. How does this relate to gravity? Do you remember this equation from Physics 7a? Yeah, some of you are yeah, and others of you are yeah, no. I rebooted at the end of the semester. I remember none of that. I get that idea. Take a look at that equation, which is the force of gravity overall, in general, and compare it to the equation at the top, and it's they have the exact same form, which, first of all, raises some questions, about the fundamental nature of things, right? You're kind of why would they? Interesting. It's odd that it comes out the same way, but also it means because the equations have the exact same form, I'm allowed to make comparisons. They are analogous to each other in many ways. So in this particular case, we still have a constant, but the force is about the size of the two masses, how much mass is there, instead of how much charge. And again, it's about how far apart they are, okay? So I can make comparisons to gravity sort of over and over and over again, and we will do that quite a bit. Well, it's going to come up in more detail later on. Just keep this sort of in the back of your mind, all right? So let's see. Let's do a calculation. Let me just show you how this works. I think that you'll be able to handle this with the greatest of ease, but who knows? We'll find out, all right? Can you read that? Or is it too small and blurry? Are you there? You don't want to tell me. One person with a thumbs up. That's fantastic. The rest of you are asleep, aren't you? What do we need to do to wake you up? I know what you would do to me, so maybe I should do the same back. Wake up! Actually, I look around and everyone looks perfectly awake. You're just kind of starey. You've entered that glazy phase where you're just in the zone where you're like, I've been listening for a while, but I'm sorry. Were you asleep? I get it. Don't feel bad about being asleep. I'm sorry for scaring you. I'm surprised you didn't just jump up and run out immediately, because I probably would have. If it makes you feel any better, like, it is a wonderful twist of fate that I get to lecture instead of having to listen to lectures all the time, because I hate listening to lectures. Which is probably why I tend to goof around a good bit and talk about off-topic things sort of intertwined with the lecture a lot, because if I were sitting there, like, no matter how hard I try, about 20 minutes in, I'm done. I've been still for too long, I am asleep. That's just the end of story. There's nothing I can do about it. You should see my notes from graduate school. I should bring them in sometime. I still have them, because every day would start with like, all right, I've got this, and I'd be like, all right, I can write that equation down. Look at that. I'm writing very neat. Things are good, But about 20 minutes in, this kind of turns into that. And then the next thing you know, it's just, And it makes me sad sometimes, because I look back at my notes from grad school and I'm like, I paid for an education. And it's like things went in my head, but I have no physical, tangible evidence that I went to class and heard all these things, because all my notes are a half a page of this and then 3 pages of that. And then the next day it starts over again. It's really sad and depressing. So, if you need to sleep, sleep. I totally get it. But I may yell occasionally to help those others who are kind of like this. You're on the border. All you need is just a little help to sort of get over the hurdle. So, these days, how often do I sit down and listen to someone lecture? Almost never. It's fantastic. It's great that I get to do this. So let's solve a problem. And good night. You go back to sleep. It's good. All good. So we've got a point charge located at x equals 0, y equals 0.3. Another point charge located, the same distance in the negative y direction. And we're going to try to find the magnitude and direction of the total electric force that these charges exert on a third point charge that's on the x-axis. So let's start by drawing a diagram. Let's see. We've got an x and y axis. Everything is happening in the first and fourth quadrant, so we'll leave it like that. We've got a positive charge that's sitting, let's say, about right here, where this is a distance of 0.3 meters. And this I'm going to call positive Q1. We've got another charge that's the exact same distance down below 0.3 meters. And it is negative, so we'll call it negative Q2. We've got a third point charge, which is positive, and it's a little farther away. It sits over here somewhere at distance 0.4, and I'm going to call it positive Q3. So to be able to do a problem like this, we have to kind of suspend disbelief just a little bit, okay? Because keep in mind that all three of these point charges exert forces on all the others and feel forces from all of the others, right? So if I were to literally drop these three charges kind of in this proximity to each other, well, they're all just going to feel a force and move somewhere else. And then a split second later, I've got a new problem, right? All the distances have changed, all the vectors are pointing different directions, and something else is going on, all right? So I'm going to have to sort of pretend that we take all three charges and fix them in position. So I can analyze the forces without worrying about them moving. So if it helps a little bit, I don't know, imagine you took these three charges, a nail and a hammer, and just like pin them down in their current location. And then we're going to see what forces are being applied to the third charge without having to worry about anything moving, okay? So we can start this problem by just looking at repulsion and attraction. So if I look at charge Q1 and Q3, and we're worried about the force on Q3 from the other two charges, well, first of all, I know it's going to be repelled by another positive charge. So the force that's coming from Q1 is going to sort of point down that direction, okay? Q2, though, is negative. So this charge 3 is going to be attracted to it, so it's going to feel a force sort of off in that direction. So the two force vectors that we're looking at, we know which direction they point, so we can just draw those in. So let me switch colors. Along this line that connects those two charges, we've got a force vector that goes that way, and I'm going to call that F13, which denotes the force from charge 1 on charge 3. There's not really a standard for these subscripts. Different textbooks you pick up, and maybe even a different day that I happen to be talking, those subscripts might get flipped the other direction. So sometimes they put the charge that's causing the force first. Sometimes they put the charge that's feeling the force first. Don't get held up on that too much, okay? If something comes up in the homework or maybe on a test and it's just not clear which way we're talking about the force, just ask, okay? Because there's not really a standard. So I'm going to use that to assume the force from charge 1 on charge 3. The other force is coming down this other direction. It's the force from charge 2 on charge 3. So we could denote that as F23 pointing in that direction. You will notice a convenience of this problem in that the two legs of both of the triangles you're dealing with are 0.3 and 0.4, which means that these distances are going to be 0.5 meters, which is kind of nice. And of course, we can find a value for F13 and a value for F23 just using Coulomb's law. And this, Q2, Q3 over R23. And we have all of those values if you just look back up in the problem. One thing you want to be careful with, you'll notice everything is given in microcoulombs. You'll want to convert that to coulombs if you want to get newtons for the force. So I'm going to go ahead and tell you what these values are. You can do the calculation yourself if you want to. Let's see. Both of those are 0.45 newtons, right? Because Q1 and Q2 are exactly the same. It also turns out that these angles work out to be the same because we're dealing with the exact same triangle. I will go ahead and tell you what those angles are because I'm sure you can find them. Let's see, I've got 36.9 degrees. So F13, F23 have the same magnitude, and they also are dealing with the same angle, which means that if I look at the x components of both of those, I could do the calculation, but we already know we're going to get the exact same value, just one's going to point to the left and one to the right. One's positive and one's negative. So we could say that the x components are going to cancel out. And if you don't trust me, work it through and prove it to yourself. Okay? But the y components are both pointing in the negative y direction and will add. So really to find the total net force, we could say F total is just 0.45 times the sine of 36.9, and there are two of them, which gives me 0.54 newtons, and we could write that as negative in the y-hat direction. Okay? It's all just vector addition once you understand which direction the forces are pointing. Questions, thoughts, complaints, issues, drops are fine too. It just disappeared. I don't know what it was, but it's gone. All gone. Any questions out there anywhere? No? Okay. So a few of these questions then. Please don't think too hard on the first couple of these. Feel free to laugh at this question. You can mock this question all you want because it's ridiculous. No, that's not mocking the question. That's mocking me saying to mock the question. It's a whole other thing. So if this force is 3 newtons, well, according to Newton's third law, the other force, the other direction, has to be 3 newtons as well. Okay? So if we carry that a little further, we already know that this is a 3 Newton force. How does force 2 change if I change one of the charges to 4Q instead of just Q? You can laugh at this question too. You doing good? You're alive? Do you want me to do that every day? Because I'm happy to, like, about halfway through, just yell once and help you out. But if you need a nap, that's cool too. Okay. Now I'm wondering if anybody's asleep over there. No, I don't see anybody. You're all doing good. I'm so proud of all you. You're very much unlike me. How do you sit still and stay awake? How? How? Is it just that much caffeine, or is it just smartphones? That's just it, yeah. See, when I was in college, we didn't have smartphones. That's a bummer. Didn't even have a laptop. Ugh. All right, so you know the answer here. If we multiply one of the charges by 4, that's just putting a factor of 4 into Coulomb's law. So we're going to get 4 times 3 is 12 newtons. How about changing the distance between the two? How's it going in the back here? Doing good? Yeah. Can I ride? Sure. Really? Like down the steps? I will die. You want me to die. Thank you. That's not very nice. So let's see. If we increase the distance by a factor of 3, there's a squared in the denominator of Coulomb's law. So, of course, that's going to make the force drop by a factor of 9 because it falls off as 1 over r squared. Which brings us to a series of questions that people typically kind of stumble over just a little bit. Okay, so we'll take a little bit more time on these. I would suggest read the question, talk to your neighbor, see what you come up with. Go. Now, are you reading? Are you reading? Are you reading? You're trying to read, but I'm talking, aren't I? Yeah? You want to throw something at me? Please do. No? Okay. Question? Symbolic. I'll tell you more in a minute. What do you think? Anybody for number 1, 2, 3, 4? Mostly 3. You're right. You can imagine putting a positive or negative charge Q somewhere in between those two charges and get it to balance out, meaning there's equal but opposite forces happening. And it turns out that right here on the next slide, you can figure out exactly where. They've given you 5 different positions. You can see that every 2 positions is considered a distance r. So that's a distance r. This is a distance r. And this is a distance r. 1, 2, 3, 4, or 5, calculate where to put that other charge such that it has equal forces. This might take a minute. And when you're done, I'm going to tell you a couple things about the upcoming exam, and then we'll be done for the day. What's that?
Yeah, exams are 26, right?
That's a good question. I have to look at my calendar.
I mean, as long as it's not next week.
I don't. Nothing has changed from what's on the syllabus. But just so I can say, the 26th. Yeah. When you think you have the answer, vote with your hands. All right, I like what I'm seeing. Number 2 there is where you can put either a positive or negative charge, plug it into that equation, you get the exact same thing in both directions. All right? We had just sort of finished up talking about the electric force and worked through a few different class questions. There are a few more of these I'd like to talk about, including sort of an advanced version of the one we just did, one that steps up just a little bit. So take a minute, look this one over, notice the differences between this one and the previous slide, and talk it out with your neighbor a little bit and see if you come up with the answer. When you have it, vote. Yeah, let's do that. Let's say anywhere on the line literally means anywhere on the line. Good question. Hello, hello, hello. Hello, hello, hello. Ooh, banana. Ugh, bananas are terrible. Anybody else in here hate bananas? Yeah? And this guy's eating one right behind you.
No, it's mine.
Oh, it's yours. Oh, really? You're eating one right behind him. That's just wrong. Bananas are disgusting. I'm sorry. Hello.
Hey,
Now, this is what you should be eating.
your lectures always make me feel real warm, so I need something to cool.
Understood. Yeah. Thank you. I guess it's just hot up here. So banana over there and ice cream over here. Whew, looks delicious. All right. What do we all think? Let me see some votes out there. 1, 2, 3, or 4. I see a lot of non-votes. Very non-committal. This may be the largest disagreement I've seen among the class so far. Usually you're pretty on target. What if I tell you the answer, and then you need to discuss with your neighbor again and see if you can come up with it? Because a lot of you are wrong. What if I told you it was this? And keep in mind, anywhere on that green line, it could be outside the charges as well. There is one region where it could work. Yeah? You agree? Like you have the answers or something. You talked about it before class. No? Yeah. Oh. I'm going to go back around this way. That scares me a little. Is that banana over there gone yet? Is it safe to come on that side of the classroom? No. No, I'm staying over here. Disgusting bananas. Oh. You're making progress. It's good. All right. Is there any of the three regions you can definitely rule out? A, B, or C? Where is it never going to happen? That was pretty good. Unless you said D, and then I'm confused. So, yeah, B is just not going to work in any way because of, well, the differences in the charge. I can't get it to balance out in the middle because one's positive and one's negative and one's bigger than the other. It's just not going to work. Is there another region where it's not going to work? You think A and C are good? Yeah. So let's talk through a positive charge. Keep in mind the discussion will work exactly the same, just flipping them, okay? If I were to put a positive charge over here somewhere, just picking a point in region C, it's going to be attracted relatively strongly to the negative 4Q charge, and it's also closer to the stronger charge than it is to the positive Q charge. So no matter what I do, I'm going to get an imbalance where the repulsive force from the charge all the way over on the left is always going to be weaker than the attractive force to the negative. Or put a negative charge there and flip them. It's just not going to work out for you because you're so close to the stronger charge. On the other hand, we could do something over here. And you might imagine now, since I'm closer to the weaker charge, I need to do something to counteract this repulsion. But there's a much stronger charge over there that's farther away. You might imagine there's some point in here where maybe I can get relatively close to that charge and sort of balance out the opposite direction forces. Where's that going to be exactly? We don't really have enough information, but it should be possible, okay? Are you okay with that now, perhaps? All right, so yes, the answer is somewhere over in region A when you're closer to the weaker charge, all right? Let's see. The next three kind of go in line with each other. So let's work through these relatively quickly. I think they're a lot easier than the last one. That is one big electron. We should draw it like tiny. But as they approach each other, what happens to the force between them all at once? Should get bigger, right? We're getting closer, so R is decreasing, so it gets larger. What can you say about which one has the larger acceleration at any point? The proton's much more massive, so if they have the same force on each other, because remember it's a Newton's third law force, that means the electron should always have the larger acceleration. And then finally, if we let them go 1 meter apart, how fun would that be? Proton, electron, let them go and see what happens. Where are they going to hit each other? Like this. I feel like my thoughts are like coming from behind me here. You're like saying the answers right after I speak, and it's like, oh, that's what I was thinking. That's weird. It should be closer to the proton side, again, because the electron has more acceleration, and the proton's more massive. It's not going to gain speed as quickly, so it's not going to move as far. All right? Which one of these arrows, 1, 2, 3, 4, or 5, represents the direction of the net force from those other two charges on the charge Q? I see people voting quickly. That's good. We'll move along on that one. It should be number 2, right? The stronger force is coming from the 4Q charge. So there's more of an upwards force than a sideways force, which is going to make it skew a little bit toward the upwards direction, which gives me a 2. And then I think that's all of those. Does anybody have any questions about any of those before we move to our next big, major, huge topic? No? Nothing out there anywhere? All right, good. So you all completely understand the electric force. You wouldn't quite go that far. I see a lot of people just sort of looking past me. You're like, I don't know what he's saying anymore. I'm going to see what's on the next slide. The electric field. The electric field is our next main topic, and it's going to stick with us for quite a long time. The first thing I want to point out is that it's similar to the electric force. In fact, it's closely related to the electric force. But it's kind of like instead of talking about the electric force, we're going to sort of just step to the side just a little bit and talk about something that's subtly different. I think it's the fact that it's so similar and so closely related to the force that it tends to confuse people. Okay? So notice the definition we have up there. First of all, I'm going to say that it's a bit of a mathematical representation as opposed to something like really, really physical that you can like see happen. It's more of a mathematical representation of how a charge will affect any other charge in the space around it. So when we say a charge affecting other charges, well, that should tell you something about force, right? We know that one charge will affect another charge. It'll either attract it or repel it. The electric field is simply going to allow us to sort of represent that force in an abstract way, okay? So a couple of different things that I need to tell you first of all. So let's relate it back to the force. The electric force is equal to Q times the electric field. So we could say that this electric field is being created by some other charge. And it exerts a force on this charge. And feels this force. Okay, a lot of words there. Let me zoom in a little bit. And then let me talk through what I'm trying to say. So I'm kind of talking in circles a little bit. So the electric field, it's in space, it's happening, it's being created by some charges somewhere, and this equation really doesn't tell me where they're coming from, okay? If I put little q, some charge, in the electric field E, it feels an effect from that electric field that's being created by the other charges. That effect is the force, the electric force that you see on the left, okay? So we could take this and rearrange it a little bit. Let's do this. We could say that F electric divided by Q equals the electric field. And remember our equation for the electric force, that was, let me rewrite it a little bit different. I'm going to write it as little q times big Q over r squared. And now we need to divide by this other q, okay? So we're taking the electric force. Remember, it involved both charges exerting a force on each other. Now it's like, I don't really want to see what's happening to both charges. I'm just trying to figure out what the one charge is doing, okay? So we're dividing out the charge that's feeling the force. We're dividing out little q, which we said is the charge that's being affected. And now we have a relationship that tells me about the charge that's making the electric field. So this is the charge creating the electric field. That point charge Q is affecting the space around it such that if I bring another charge nearby, it's going to feel a force, okay? Let me relate this back to gravity one more time. So let's see, the gravitational force we said was G, and I'm going to write it a little different this time. We'll write it as little m times big M over r squared. And we can do the same sort of progression, right? I could divide out the mass instead of the charge. Now we've got those m's canceled. And then we've got something new, Fg over m. What in the world is that? Not really anything that we talked about, per se. But you might relate it back to the gravitational vector, right? The acceleration due to gravity. And if you did the calculation, you'd see that that fits and is true. And it's equal to capital G times big M over R squared. So you can see that this big M is creating a gravitational field around it. And we already kind of understand that, right? If I have a mass, let's say that maybe that's the Earth, we understand that there is an attractive force that is everywhere around it, and we understand that that's there whether or not it's actually pulling on another mass, right? I think we understand that there is gravity in the space around the Earth. We only see the effect of it if I take another mass and put it near the Earth and say, oh, look, they're being attracted to each other. And if one mass is much bigger than the other one, we see the one mass that's primarily attracted to the larger one, okay? So here's a way to think about it. The electric field is about points in space. What is happening at those points in space? The electric force is what we get when we take a charge and put it at that point in space and let it feel the effect of the electric field, okay? Or, related back to gravity, see this point in space? Ooh, see it right there? It's a very nice point in space, don't you think? I like it. It's really hard to see. It kind of makes me cross-eyed a little bit. Do y'all like this point? It's very nice, yeah? There is gravity passing through this point right now, right? A gravitational vector that's essentially pointing straight down. It's there whether or not it's currently acting on anything, okay? I lost my point. Anybody see it? Help? And it's like right here somewhere. I don't know. So there's the point in space, right? If I take this pin and put it there, now we get a gravitational force as soon as I put it in that spot, okay? So think of it as an abstraction, right? The gravity is there, whether or not I actually let the gravity do something. The electric field exists around charges, whether or not I put another charge there and let it do anything. You see the difference? Are you okay? Can you nod a little bit? Or even like you can shake your head too if you're just like, I don't like any of this. This is terrible. Yeah, some of you are kind of like, you can't really say which way your head should go, okay? The electric field is an abstraction of the electric force. Before I go further, let me just say that this next part, the last time I taught it, for some reason went sideways. It's like all of a sudden everyone is in confusion land and I don't know what happened. So I'm going to warn you in advance because like maybe if you prepare yourself, you're like, okay, here it comes. I am not going to be confused. It's almost like bracing yourself for impact, right? And then you'll get it because you were ready to absorb something that I said might throw you off, all right? Notice, we have an equation already here at the top. I turned around to write and nothing was there. So let's go over here. We've got an equation that tells us about the creation of the electric field from a point charge. And we've got an equation that relates the electric field back to the electric force, all right? So we can find something about the magnitude of the electric field, but what we don't have really yet is the direction. The direction is found by using something imaginary known as a test charge. Notice it's got air quotes around it a little bit. It's like a test charge. What do we mean by a test charge? A test charge is something that we're not actually going to put in the problem. We're just going to sort of drop it in our mind, and we're going to pretend that it's really, really small. It's always going to be positive, and we're saying that it's so small that it's not really affecting the problem. In other words, we're not going to worry about the electric field that it's creating. We're ignoring its effects. So if I want to find out something about the electric field at a point in space, I'm going to imagine what would happen to an imaginary positive charge if I put it in that point, okay? So in other words, back to gravity, there's my point in space, right? And I'm like, ooh, the Earth is down there. I see it. I know there's gravity there, and we already know which way it's going to go because it always goes the same direction, right? It's attractive, unlike the electric force, which could go either way. What we want to do is, like, think about that point, like, stare at it, and be like, I'm going to imagine putting a mass there and which direction it would feel a force. So it's like, oh, I see the point. I can imagine putting a mass there. And if I put the mass there, I know it's going to get pulled that direction. that would tell me the direction of gravity at that point. When we're dealing with the electric field, maybe we go up here to the top and we're looking at this point P, and maybe that point P is somewhere near a charge Q. What we want to do is imagine putting a tiny little positive charge there and imagine which direction it would feel a force. So we know if this is a positive Q in the middle, if I put a positive charge at point P, I know it would get repelled. So that tells me the direction of the electric field at that particular point. And then you could keep doing that, right? You could just continue to be like, ooh, what if I put an imaginary charge here that's positive? Maybe here is like over there somewhere. Now I'm talking about that point. I know that it would get repelled that way. And I can continue to do this, and we would be able to draw the fact that this electric field is always pointing away from a positive charge. And we would need to do that at every single point in space to sort of be able to plot out what the electric field looks like at all of those points in space around it. All right? Now, if you're thinking, wait a minute, that could have just as easily been a negative charge. Yes, it could have. But at some point in the past, everyone agreed on a standard just to keep everyone on the same page. And we decided that the electric field would be defined as the direction that a positive charge would be pushed or pulled at those points. Okay? So don't think of this as something that has physical significance. It's just like the definition of positive and negative to begin with. Just to keep everyone on the same page so we could agree on the direction of the electric field, we use a positive test charge to examine it. Okay? Are we okay? Are you mad at me or anything? Do I need to apologize? No? Do you need to apologize? You're like, yeah, I was looking at Instagram. I need to apologize a little bit, but I don't care. Look at Instagram all you want to. Let's see. What else to say about this? There is more. By the way, notice it is a vector like so much else that we do. So just like with the electric force, if we have multiple charges and we want to see what the total electric field is at a point, we're going to have to use vector addition. We're going to do an example of that in a second. Just keep in mind that you always have this connection F equals QE to go back to. So if you have a problem that asks you for the electric field at a point, and then later in the same problem says, what's the electric force on a charge at that point, you don't need to do all the calculations twice, right? If you have found the electric field everywhere, essentially you found the electric force on any given charge everywhere, okay? They're not two separate calculations. They're intricately connected to each other. So if we were to, hold on, let's see. I don't want to do that yet. Tell you what we're going to do. I'm going to hop over to something else. Woohoo. Electric fields from point charges. See our beautiful point charge there? It's a positive 1, it looks like. Yeah, okay. Let me zoom back out a little bit so I can get controls back. Oh, no. I zoomed in too far. All is lost. Maybe all the way at the edges. Nope, can't do it. We're all stuck now. So what we're going to do is close that. Ooh, that was pretty. And reopen it. Okay. We can put the electric field around that. And notice, there's just one charge there. It's doing something to the space around it. It's a representation of what would happen to other charges in its vicinity. In this particular example, notice they're using how strong the color is to sort of represent the strength. As we get closer to the charge, it's a stronger electric field. And then they're fading it away as we get farther away because R is getting larger. It would be better represented to keep with typical vector notation and have longer vectors to indicate a stronger force. So if it helps, imagine that the ones really close nearby are really long, and as I get farther away, those vectors are getting shorter. Okay? So we could do a bunch of things. First of all, ooh, that's just fun. Let's add another charge, though. Ooh. And there's actually a force being drawn here as well. I don't know if you can see it, but you see the tiny little vector sitting right next to the 3? Can you make that out at all? There is a vector there. Notice they're going to draw the force as well by letting that vector expand as I get closer. And you can see the force on the two charges as well, okay, as those fields interact with each other. But, of course, we need to add a negative charge and see what happens with that. Ew. I'm just going to play with this for the rest of the hour. Is that okay? Okay. It's kind of mesmerizing, no? Yeah. So, of course, the electric field vectors are going to point toward a negative charge, because if I imagine a positive charge being nearby, it's going to be attracted. So by definition, the electric field always points away from positive charges and toward negative charges. And of course, that can turn into a really complex field of vectors as I add more and more point charges. But don't forget that this is actually happening in 3 dimensions, right? Everything we had there before, that's just an XY plane. Don't forget this is radially happening around the charges. And in the case that we have here, we apparently have a negative charge. All of the vectors are pointing in, and this one we can turn. Ooh, yay, fun. And I can do other things too. Let's do more things. More field. More vector density. Oh. Now the iPad is starting to say, don't make me calculate that much. I really, look, it's all stuck. Stop. There we go. We'll turn it down a little bit. Okay? You get the idea, all right? But it's fading away and getting weaker as you get farther and farther away. Who's got questions before we do an example problem? Anybody? Nothing? Are you okay today? Just extra silent? Maybe? You understand everything? You are the voices in my head telling me that all is well? Yeah, okay. You know, I'm thinking about experimenting with you guys. How would you like to be experimented on? Not today, but in the near future. You're like, yes. Yes, you want to be experimented on? I haven't even told you in what way. You're like, I don't care. Medical experiments, give me pills, like whatever. Just like, yes, I'll be experimented on. I was doing a little reading last night because I'm of the firm conviction that an hour and 20 minutes is way too long for a class. Anybody agree? Uh-huh. It's way too long for all of you. It's way too long for me. Typically, I think 50 minutes is just about right. It's almost like you can maintain high intensity the whole time. It's like, ooh, we have to learn. And then the next thing you know, you're like, oh, we're out of time. And the students can almost stay with that as well, okay? And I've even noticed in here, like as we approach the 3 o'clock hour, like all of you start to kind of, like this. And I kind of feel like I'm wrapping up. And then I look down and I'm like, oh, we got 30 minutes left. Yeah, it's too much for all of us. So I was just doing a little reading last night, like ways to break up a long class. What can we do, And there were some interesting thoughts and interesting ways we could experiment and try to just like really see at what point you people lose it. Including like some apps where we could maybe put a screen up here and just like when you're just like, yeah, it's too much. Like I'm ready for this to end. Like maybe you could just click a button on your app and your seat would light up. And then we could just kind of track, like as seats turn red, like how far are we into the class? And at which point am I like, oh, we need to just stop for a minute and like completely regroup because everyone's losing it. And then maybe you'd all turn back green after a few minutes of relaxation. I saw someone suggest that every 15 minutes you should have 5 minutes of tech time where it's like just boom, just scroll through whatever feed you want to for a couple of minutes and then come back and we all get refocused. One that I saw that I liked that I don't know that you would like as students because I'm not sure I would like it was to set a 10-minute timer. And every 10 minutes it rings and then I pull a person out of a hat and you have to do one of 3 things. Ask a question about the material, or maybe ask me a personal question, or we could come up with a number 3. I don't know what number 3 would be. Any thoughts? Maybe you have to run a lap around the classroom. Yeah, you want to run the lap? Just yell. Just scream as much as you want for 2 minutes. I could get into that. I may step out for those 2 minutes if that's okay. So I don't know. We may try some things in the future that you may or may not like and that may completely bomb, but I get it. I understand. I've told you before that I'm good at listening for about 20 minutes, so it's tough. I understand it. Let's do an example problem, all right? And then in a few minutes from now, we might do something. I don't know yet. 2-point charges are on the x-axis. The first one is positive 16 meters from the origin on the positive x-axis, and the second one is also positive, and it's on the negative x-axis. So let's draw a quick diagram and get everything in order here. Let's see. X-axis, y-axis. Yay. We've got one that is over here. Let's call this Q2, And the one over here we'll call Q1. Q1, it said, is 16 meters along the positive x-axis, and Q2 is 9 meters along the negative x-axis. We're going to add to this a point A, which is going to be about right here. And we're going to say that it is 12 meters along the positive y direction. We are going to, first of all, find the total electric field at point A. And after we do that, I'm going to add to this question just a little bit. The total electric field at point A. So, because this is a good bit similar to what we did with forces, I'm going to skip over some steps and kind of rush through this just a little bit. But remember, at point A, there is no charge right now. Nothing is there. We're trying to find something about that point in space, specifically the direction and magnitude of the electric field. So I need to imagine putting a positive charge in that place. And imagine which way it's going to be attracted or repelled by the other charges. So since the other two are positive, we know it's going to be repelled by Q2, and along a direction directly opposite from it, it's going to be repelled by Q1 along a direction exactly opposite from that. So let's fill those in. Let's see. I'll draw a line from Q1 over to A. We've got that, which we will call electric field from charge 1. And then we've got this electric field going this direction. We'll call that E2. You can find E1 and E2 as well as its components in the X and Y direction. So let's go ahead and break those into components. This would be E2X and E2Y. And this one would be E1X and E1Y. Because we have all the sides of various triangles there, we could call this one theta, which is also going to be that angle. We could call this angle phi, and that's also going to be that angle. And then we can, first of all, calculate magnitude. So E1 is going to be KQ1 over R1 squared. And we're given the magnitude of Q1. R1, well, we could find it because we have all the sides of the triangle, so we could find that as needed. I'll go ahead and tell you what that is. This one's going to be 20 meters, and this one over here works out to be 15 meters. So we've got 9 times 10 to the 9th times Q1, which is 8 nanocoulombs, and R1 is 20 meters. So E1 works out to be 0.18 newtons per coulomb, and you can do the same thing for E2, which works out to be 0.24 newtons per coulomb. Nothing too hard so far, okay? Taking a look at everything that's happening here, Q1 and Q2 are different values of charge. They also sit different distances from the point A. So just at face value, I don't really have any reason to suspect that, say, the X components are going to cancel out. We'd have to do the calculation and see what happens. But we do know that the Y components are both pointing in the positive Y direction. I will just write down these answers and let you do the work. First of all, we can say that E1X works out to be minus 0.144, and E1Y works out to be 0.108. And E2X and E2Y work out to be 0.19 for E2Y, and weirdly enough, 0.144 in the positive direction. So even though it didn't look like the X components were going to cancel out, once you do the calculation, they actually do. So EX works out to be 0, and EY, it looks like, works out to be 0.298 newtons per coulomb. So we could say that the electric field at point 8 is just 0.298 y hat newtons per coulomb. So if we were to go back and draw in that electric field, it's pointing directly up this direction. Easy enough? Maybe, yeah. Questions, thoughts? Now, of course, if we wanted to find the value of the force on any charge at that point, all we have to do is use F equals QE, right? If I know the electric field at that point, I can multiply it by any charge I drop at that point and find out the value of the force on it, all right? So you don't have to do those calculations again. Let's add a second part to this, though, and find, let's see, let me write this out. What charge would be required to give E equals 0 at point A? If this third charge were placed at 0.15, what charge would be required to give E equals 0 at that point? If we place it 3 meters above point A along that same axis. Banana's gone, right? Bye-bye, banana. Yeah. It's probably in the trash can now, which means that's just going to smell for a while. Bananas. Please tell me there's more of you that hate bananas. Bananas? You all love bananas, except like me and you, right? We hate bananas. Other banana haters out there? Yeah. You hate bananas, but you're being volunteered. Anybody else? Really? They really are disgusting. You know, I think I personally have an issue with it because I was a sick child, and I'm told that when I was like 2, the only thing I could eat was bananas for some reason, so I think that developed into something later in life, because now it's just like bananas, like they're squishy, and you have one in there, don't you? You're
Not Chipotle, something else to eat.
well, you know, I don't hate it. It's just question.
How many sides does a banana have?
What?
How many sides?
How many sides does a banana have? I don't want to waste my brain cells on thinking about bananas. I don't know, 4?
It's 5.
It's
Although
5?
25% of the time it's 4. Yeah, I know.
That's good to know. Interesting. I'm just going to trust you on that and just assume it's not completely fake.
Because you said you buy me a banana by accident. So.
Really? Huh. We all learned something today. Not about this, but about bananas. Huh, who knew? So let's see. We're going to put another charge here. Let's go to another color. We're going to put that other charge at about that point. That's where Q3 is going to go. And if I'm going to cancel out the electric field at point A, I essentially need to create the exact same electric field pointing in the opposite direction. So I need Q3 to create 0.298 in the negative y direction, and then there'd be no net electric field at that point A at that point. So we could say this, E3 equals KQ3 over R3 squared. And we can rearrange that for Q3, which is going to be E3 times R3 squared over K. And we need E3 to be 0.298. We need it to create the exact same electric field, but just point down instead of up. So you could solve that. We're going to use 0.298. This would be 3 meters. And K, of course, is 9 times 10 to the 9th. And you should get 0.3 nanocoulombs after you do the conversion at the end. Okay? So dropping a third charge and keeping them all in those positions creates an electric field such that at point A, it all adds to give me 0. Okay? So another question might be, well, what happens at that point if I take a charge 4 and put it at point A of any value? Assuming charge 4 is infinitesimally small, what's it going to feel? What's the electric field at point A? It's 0. So if I took another charge Q and multiply it by 0, at that point, if we assume it's really, really small, it feels no force. It's almost like there's a point there in space that's like, oh, like even though there's all these charges around, there's like a little blind spot. There's a sum of zero electric field at that point, so another charge would feel no force at that point. It would be sort of perfectly balanced out. Okay? Questions? Good. I've got questions for you. There's one. Go. One, two, three, four, five. That's like, I don't know what that is. You've got two fours, so it's 8, and an X. 8X is your answer. I don't think that's an option. 4 should be it, right? We're doubling the numerator and also doubling R, which gives me a factor of 4 in the denominator. So that's going to be a result of a half. And then we have another one of these slides that I have to apologize for. Does anybody see an issue? Yeah, there's some problems going on here. So very many problems. So first of all, if you have, well, it's like different waves of laughter. I like that. It's like something about reading speeds, perhaps. I don't know. So if you have any color blindness, I apologize for this immensely. Okay, so let me try to fix it a little bit. So the word blue seems to be an orange. So this is blue, and this one is blue. I think this is another type of test. It's like on top of physics, you have to have some kind of weird. You're taking pictures of this because it's just that bad. I understand. It's like, hey, look at this thing my teacher showed me today. Like, this is the worst. The blue word is actually green, so that's green. So this one is green, and this one is green. And it looks like red is actually red. Did I miss anything? Okay, so what we're trying to say is that the charges on the left, the positive 1 charges, are both creating an electric field around them, and we're trying to determine whether the +2 or the +1 is feeling a greater electric field. Which one is it? I don't know. I'm confused with my own colors. Maybe we should like color these in, make it better. And green. And I'm going to make those blue. So the key point here is it's not about both the charges, right? The positive 1 green charge, the one on the left in both cases, is creating the same electric field no matter what the other charge is, all right? So we could say that both the red and the blue charge experience the same electric field from the green charge, all right? The difference lies in the same colors. Again, I'm not going to fix it this time. Which one experiences the greater electric force? Well, that does depend on the charge you put in that spot. So the one with the +2 is going to feel the greater electric force. Same E, different Q gives me a different F. Okay? Question. I understand this is terrible. All right, so I'm going to add a couple of things to this real quick. Let's see. So in this case, you can imagine that this positive 1 charge is creating the exact same electric field around it. Okay? So the positive 2, the red charge is sitting in that electric field, and the blue charge, or the orange one, is sitting in the exact same electric field because it's near the exact same charge. However, they will experience a different force because they have a different magnitude themselves. Yes? I called the red charge blue. Oh, man. Thank you. Yeah. Yes? Well, all the charges are feeling a force, okay? But if we're specifically asking about this one and this one, which one feels the greater force, it's the larger charge, the +2. So this one feels a greater force, even though it sits in the same electric field, okay? And we could relate that back by F equals QE. That is the same. This is larger. Okay? Anyone else? Question? Yeah, totally. You could just solve this directly, not using electric field at all. Yeah. The point is to compare the two slides and see how it relates back to the electric field. Yes, you are correct. So, this one. What is the electric field at the center of the square that you may or may not be able to see? Can you see the square? A little bit, maybe? What is the electric field direction? 1, 2, 3, 4, or 5, all the way over here for some reason, as a fifth option? Or is it 0? All right, so if I put a positive test charge at this point, we know it's going to be attracted this way, and it's also going to be attracted that way. If I add those two vectors together, they should be equal vectors, which is going to sum to give me 3. The vertical component should cancel out. What if we put the same charge on all 4 corners? Yes. You finished your ice cream, haven't you? And it gave you a lot of energy. Yeah, fantastic. See, the banana people over here, you look sad. See, this is the difference. Banana, ice cream. We should put you on a slide next to each other. It's like, oh. So, yes, we would get vectors that are equal in all 4 directions, and they should cancel out and give me an electric field of 0 at the middle of that square. What if we put different charges at 3 corners and ask about the 4th corner? This one might take a little bit more time. So let's see. Starting with the charge on the bottom left, it's going to create a repulsion at this point. This charge at the top is going to create a repulsion that way. This charge, the negative one, is going to create an attraction, but notice it's farther away. Okay? So that means when I add these two vectors, I'm going to get something in the direction of 4. And then we'll have a little bit subtracted from it, but not enough to cancel it out. So we're still left with a vector in the direction of 4. Okay? Maybe. All right. And I think there's just, how many more of these are there? Why are there so many questions? Okay, I'm going to stop there for just a second. I want to tell you about another thing that was in the list of suggestions. Okay? Because it makes me think of myself a little bit, and I was like, I can't do that one. It won't work. It's like it said, be like smile a lot and be like friendly, and I'm like, it's like be really like conversational. It's like I can be conversational, I can do that, but like smile. See, here's the problem. I've learned that when I think I'm smiling, I'm not, and it really makes me sad because I can't fix it. You too, or you're just like, yeah, I've noticed that about you. I understand because. One day I was like in a drive-thru somewhere, right? And it's like I ordered something. I get to the window. I'm like, thank you very much, right? And they hand me the thing. And I happened to catch my reflection in my mirror at the time I said that. And I thought I was being like really warm and like, thank you. This is great. Thank you for. And I look and I'm like, I look like an absolute idiot. Like, what kind of mean person would drive through a drive-thru and look like that at somebody? Like, I'm just surprised. They probably turn around and be like, they give him the food, doesn't even smile at me. I was like, I was smiling. So I don't know how to fix this. Like right now, here's a smile. Am I smiling? A little bit? I think it's in the eyebrows, right? You have to raise your eyebrows. Is that the key? How do you smile? Help me. Because if you're not careful, it does turn into like, hi. No? Okay, so I just want to let you know, though, like if you're like, he's really like kind of mean and standoffish, like I'm smiling on the inside. If I can't get it to my face, I don't know what the problem is. So what's happening here? I don't know what's wrong with those circles, first of all. Just imagine there are point charges Q1 and Q2 there, creating the electric field that's pointing straight down in between them. What can you say about those two charges? And yes, they are supposed to be equidistant from the axis below. So the fact that the vector is pointing down in the general direction of the charges should lead you in the negative direction, because a positive test charge at the x is going to be drawn to negative charges. And the fact that it's pointing straight down in between them should lead you to the idea that those charges are equal. If the left charge, Q1, was stronger, then that electric field vector would lean more in its direction. Okay, so it would point a little bit more toward the stronger charge when you add the vectors. Which brings us to one last one. We have this electric field that is quite invisible, so I'm going to draw it in. There's an electric field here, and that charge Q is sitting inside it. So we're pretending that electric field is coming from somewhere else, and we're dropping a charge Q inside it. Notice it says that we have a 4 Coulomb charge. It feels a force of 12 newtons. That should tell you something about the electric field, right? First of all, we can say that the electric field is going to be 3 newtons per Coulomb. Yes? Good so far? So when I drop a different charge inside, a 6 Coulomb charge, we can multiply that back the other direction, and we'd understand that it's going to get 18 newtons of force. This is trying to point you to the fact that that the charge Q, we're sort of ignoring how much electric field it's creating, and we're saying that we're putting it in an electric field created by something else, and it feels a force in response to that. All right? So we are going to take this calculation to the next level just a little bit. Point charges, well, they're kind of boring in a way, all right? And also, we can't really go very far. You can imagine, like, if I put a few different point charges in some different places and then said, hey, find the electric field out at this point, well, that's kind of enough work, right? You don't really want to do much more work than about 3 charges. If I start to increase this a little bit, then maybe even throw in a negative, all of a sudden it's like the exact same calculation, but it's like, well, it's a simple calculation. Just let a computer do it, all right? It's the exact same thing over and over again, KQ over R squared. For every individual charge, just add the vectors. So what happens if we want to deal with more complicated situations where there's so much charge where really I can't even tell how much charge is there? In other words, maybe something like this. Maybe we have a bunch of charges that are sitting in a line. And just to help me out, I'm going to draw a long rectangle, and then we're just going to start filling it with charges. So maybe inside here is a bunch of positive charge. Ooh, you get the idea. There's so much there that, let's go back over the top of it again. Ooh, like I can't tell how much is there. It's full of positive charge, all right? There's some total amount of charge, but maybe I don't even know how much that is. Well, if I wanted to find the electric field down here somewhere, it's still possible to use KQ over R squared. It's just going to take a while, right? So I could be like, okay, I know there's a positive charge there. I need to know that distance, do the calculation. And I know there's one right next to it. I need to do that distance and do the calculation. And we could continue to do that for every single charge that's on that line of charge and eventually get to an answer. It's going to take forever, okay? So instead, what we're going to do is we're going to break this up into infinitesimal pieces of charge, dq, each one of which is going to contribute to the electric field at some point away from those charges. So if this is point P, we know that that dq creates an electric field that we would call dE. It's a little bit of the total electric field. So we are going to use the same idea, the point charge equation and calculation, but we're going to use a differential form that we can integrate instead. So in other words, we are going to say that dE is equal to K dQ over R squared. And to find the total electric field, of course, we're going to have to integrate that equation. All right? And you can imagine a bunch of different ways we could have charge sort of spread out. Here, I've illustrated a case where maybe I just have a bunch of charge that's in a straight line. We could have charge that's formed like and spread across maybe the surface of a sphere. We could have charge that's like maybe along a circle, along a hoop. There's a bunch of different configurations we could have charge. We could even maybe take this thing, right, and wrap it up into a pretzel and be like, well, what's the total electric field from the pretzel of charge some distance away? And all of a sudden you might start to think, ooh, these calculations could get hard, they could get complicated. It all sort of depends on how the charge is spread out and distributed. We're only going to be able to take that idea so far, all right? So we're going to look at two basic examples to kind of give you a feel for how things work. You will be asked to do some things that are harder than that, but there will be limits as to what we can do in this class, all right? Also, keep in mind that everything that we're doing here is finding the electric field at one point, which is kind of depressing, right? I've drawn one point here that's some distance away from all that charge, and I can work through this integral and find out the total electric field at that point. But then all of a sudden, like, ooh, what if I need to find the electric field over here? That's another long and involved calculation, okay? Every point involves something different. So when we get to the next chapter, we're going to look at a way to simplify this, okay? So we're going to be able to take this so far, but there are some more complicated things we can do using techniques in the next chapter instead that will allow us to do those more complicated calculations, all right? For now, let me give you three things that you're going to use when doing electric field for continuous charge distributions. First of all, we are going to use symmetry as much as possible. So we'll say use symmetry to reduce complexity. In other words, look at the problem at the start and specifically look at the different components of the electric field and try to figure out if something cancels out. If something cancels out, fantastic. You don't have to do that part of the calculation. Number two, we are going to re-express dq. So express dq in terms of a charge density. Express this little bit of charge in terms of a charge density. In other words, this is kind of equivalent to, did you guys do fluids last semester? Yeah, a little bit. I can't tell from your answer. You're like, yes, in 7A last semester, those of you who took that class did fluids. Okay, good. In that particular case, like, we went from talking about mass over to density, right? Because instead of having like a piece of mass that was maybe moving from point A to point B, when I dealt with a fluid, it's like I had all of this mass that was just kind of everywhere. It was easier to do all the calculations talking about how that mass is distributed throughout the volume and talk about density instead of trying to deal with every little piece of mass in the fluid. That's what we're doing here with charge. Instead of dealing with every individual charge, I'm just going to look at how the charge is packed into a space and look at its density instead. And by doing that, we can do the calculation a little bit faster, okay? So there's three different charge densities that we're going to use over and over and over again. First of all, the linear charge density. So if all the charge is essentially along one line, it's in one dimension, it's like one charge after one charge after one charge after one charge, we could express a linear charge density, and typically lambda is used for this. And it is simply all the charge that's in the line divided by the length over which that charge is spread, the linear charge density. And that diagram on the left, well, we would use a linear charge density there. If I could figure out how much total charge there and what the length is, we can figure out how it's packed into that length. You might guess that we can step that up to 2 dimensions and talk about an area or surface charge density. So if instead of all the charge being in a straight line, if you imagine we had a bunch of charge that's spread out along a surface or along that tabletop at the front of the classroom, right? Charge is all across a surface in some way. Typically for this, we use sigma, and that's going to be the total charge divided by the area over which that charge is spread. And C, we can step that up to 3 dimensions and deal with a volume charge density. And I think you can guess what that equation is going to look like, but I will tell you we use rho for this, and it is Q over V for volume. And then there's the stray dot down here we're going to get rid of. Here's the thing about these charge densities. This isn't the only way we're going to write these 3. Notice at the top it says continuous charge distributions. By continuous, we're also meaning that it's kind of the same everywhere. Okay? There's charge that's spread out in a continuous way that it's not really broken up, but every part of it has the exact same density. So that means instead of talking about the total charge and the total length, volume, or area, I can take any piece of it, and I should get the exact same calculation, which means I could rewrite all of these as dq over dl, or this one could be dq over dA, or this one could be dq over dV. We could also look at infinitesimal bits of the charge and the length, area, or volume over which it is spread, and we should get the exact same ratio. Okay? There is a number 3 that I need to add to this, unless you have questions. Questions? No? Good so far? Questions? We are going to, in the end, check our answer at extremes for validity. And by extremes, typically this will be either 0 or infinity. And it might be, let's just use r, some distance away, 0 or infinity, and just see if it makes sense. See if it agrees with what you would expect the result to be based on everything that we've learned so far, and you'll see how that works in just a little bit. This is the way these problems are going to set up. Are you ready to do one, and then we'll call it a day? Yes? Maybe? Was that yes for you'll be ready to call it a day, or you're ready to do one? See, I can't tell. I should ask one question at a time, shouldn't I? That would make a whole lot more sense. So let's look at a line of charge. A line of charge with a linear charge density. This time we're going to position it vertically. And we are going to try to find the total electric field at some point P that is a distance x from the midpoint of the line of charge. We're only finding the electric field at that one point, okay? So we should add to this a little bit. We would say that it has a positive linear charge density, which it doesn't help that I put a negative right next to that, so let's change it to an arrow. And we are going to find the electric field at distance x from the midpoint. Okay? Notice they have specified a little piece of the line of charge at the top. So first of all, just keep in mind, like, there's a bunch of positive charges that are sort of all lined up down through here. And this little piece of the length, they're designating as dy because it just so happens that the length of this thing is in the y direction or along the y-axis. So instead of L, we're going to use y, first of all. There is some charge that's contained in that little piece of the linear segment of charge that's going to create an electric field over at this point. And you'll notice which direction they've drawn the electric field, because if I imagine putting a positive charge there, it's going to be repelled by whatever positive charge lives in that little piece, okay? So that electric field is going to point directly away from that in this direction. You can imagine if I go all the way to a corresponding point down here and look at a little piece dy, it's going to create an electric field at point P that, well, is exactly equal but up in this direction. Agreed? Which means that for just those two pieces, this dEy, the y component there, is going to cancel out. And we can do that for other pairs of segments along this wire. For every little piece here, there is a piece down here somewhere that creates a corresponding electric field vector in the opposite direction. Okay? So we're always going to have y components that are going to cancel out. So let's go ahead and put that in here. We could say that dEy all cancel out. But you'll notice no matter where I am on that length of charge, we always get an x component of the electric field that points to the right. And they're all going to sum up and add. So we are going to have to worry about the x component. So dEx, all in the positive x direction. Everyone still good? Am I smiling? Kind of? Okay. Maybe I'm getting better at it. I don't know. Kind of is a lot better than it used to just be like, no, you're not. Why are you so angry? What's wrong? That's as good as I can do. That hurts. I don't want to do that anymore. All right, so let's go back to this equation. So dE is going to be equal to K dQ over R squared. And first of all, we're only worried about the x direction. That's the only thing that's going to contribute. So if I'm worried about the x direction, we could rewrite this as dE x, which is going to be K dQ over R squared cosine theta. If we go back over to the diagram where they've drawn theta, we could also put the theta here, and the cosine of that angle gives me the x component. We need to re-express dQ. Okay, so we can say that lambda, since it's a linear charge density, lambda is Q over L. We already determined that L is in the y direction this time, so I could write that as Q over y if y was the total length. Or we could write that as dQ over dy and then rearrange that to solve for dQ. So dQ is lambda dy, and we're going to plug that in. So dEx is K lambda dy over R squared cosine theta. Ew. I don't like the looks of that at all. Okay? So let's see, what else to do with this? First of all, we want the total electric field at this point, which is going to be the integral of all this stuff. So the integral K lambda dy over R squared cosine theta. A couple of things are constant. The K and the lambda are constant, but that still leaves me with y, r, and theta as variables. Not a whole lot of fun there. All right, so let's pull those out. E total is K lambda, it's the integral dy cosine theta over R squared. And then you're going to have to make a few substitutions. Any thoughts or ideas? Yeah? I like that. Okay, so let's do a couple of different things here. We're going to try to get everything in terms of theta. And to do that, we are going to have to make substitutions for this and this, part of which is going to be what you said there a second ago. Okay? So let's see, dy. So we could first of all write tangent of theta is y over x in this diagram. Or in other words, y is x tan theta. And then we'll take the derivative of both sides, which gives me a dy that we can substitute in. So we could say that dy is going to be dx tan theta. The distance x is a constant. We're always the distance x away from the line because we're only looking at that particular point P. So I could rewrite that as x d tan theta, which gives me a secant squared. Oh, I'm all sorts of out of space here. So now we've got x secant squared theta d theta is equal to dy. And then because we have that other cosine there, I'm going to change the secant squared into 1 over cosine squared. So that means dy is going to be x d theta over cosine squared theta. So there's one substitution we're going to make. Hey, look, the next slide is all about the same problem. So I'm going to use some of that space over there, all right? So let's go back over here. We've got E total is going to be the integral of what? K lambda integral dy cosine theta over r squared. And our first substitution is that dy is x over cosine squared theta d theta. So that's going to go in there. The other substitution we're going to make is, let's see, we can say that cosine theta is x over r in that diagram. Yep. Which is the same thing as x over the square root of x squared plus y squared. And we can square that, so we get cosine squared theta is x squared over x squared plus y squared. And then we'll rearrange that for x squared plus y squared. So that's going to be x squared over cosine squared theta. And don't forget, x squared plus y squared is r squared in that diagram. The hypotenuse squared is x squared plus y squared. So we're going to plug that into the denominator, and then everything will be in terms of things we'd like it to be. So let's see. We can say that E total is going to be K lambda times the integral of what after everything cancels out? I think the only thing left in there is a cosine. Did that work out for you? Someone plug all that together. Stuff cancels out? Yes? Okay, so substitute in for the r squared, x squared over cosine squared theta, and substitute in for dy x d theta over cosine squared theta. The only thing left is a cosine theta. So once we do that, we need some limits of integration. How do we get the entire line? We are making an assumption that this distance x is a whole lot less than the entire length of this line of charge. It doesn't really look like it in this particular diagram because they've kind of exploded it out so you can get a good look. But imagine that perhaps like the entire line of charge looks like this, and this distance x is actually kind of like right here. We're sitting right next to the line of charge. In other words, it's almost like the line of charge is the front of this table, and I'm like right here trying to measure the electric field, okay? If that's true, if x is much less than L, then looking all the way to one end of the line of charge and to the other end is almost at right angles from my position, okay? So we're going to make this limitation and say that for x much less than L, we're going to go from negative pi over 2 to positive pi over 2, from 90 degrees to 90 degrees. So this result is going to work for x much less than L, or it'll simply work if the line is basically infinitely long, okay? Question? Question here then? You have a leftover x. I see that x. There shouldn't be a leftover x unless I wrote one of those steps wrong. Let me double check. Aha, I found the x. You're right, there is an x there. And it is hanging out outside the integral because it's a constant. Okay, there is an extra x in that denominator. My apology. So we don't actually want the x there. So look down here at the bottom. That's a good point. Was that your question over here as well? Someone else had their hand up as well. Yeah, there is another x, and because x is a constant, it's sitting outside. Okay? Thank you for pointing that out. It is written right here, and I just completely didn't write it down. All right? So going from negative 90 degrees to positive 90 degrees for the limits of integration, once you work that through, we are simply going to get what? It looks like we get a 2 out of there. So this is going to be 2k lambda over x once everything is done. Okay? The antiderivative there is sine, and we've got that negative 90 degrees. You're going to end up with 1 plus 1. Any questions before I wrap this problem up? In the back. It's all because of this assumption. We're assuming we're really close to the wire. So if x is really close to the wire, imagine, let me go here. X is right here. To integrate starting all the way at the top of the wire, this theta has become almost vertical. And to get all the way to the bottom, it's almost vertical. Okay? Any other questions? What was the third thing in the list? The third thing in the list. Checking for various limits here. So what happens if we get very far away? If x goes to infinity? It gets really small. I think that sort of makes sense, right? If I'm a long way away from this line of charge, I really shouldn't feel any effect from it. There should be essentially no electric field at a great distance. What if x is 0? If x is 0, I'm literally in the line of charge. That really has no meaning at that point. I've gotten too close, so it makes sense that that's going to blow up and things not make sense. All right? So it seems like our answer has limits that seem to make some sense. We have 4 minutes left. I'm not going to keep talking, so it happens. All right? So for starters, let's see here. We had finished this problem where we're looking at continuous charge distribution. So instead of just multiple point charges, we're almost treating it like there's an infinite number of point charges that are all arranged in some specific way, all right, which requires using the point charge equation but integrating over some space. I see a question back here. Different people will come to class. I'll probably bring more or find an electronic way to assign numbers or something. I just didn't have time. So if you want to keep it, go ahead. I don't mind. You really like your number, don't you? It's okay. So let's do another problem. All right, we finished this one. And let's rearrange this charge. So in this particular case, instead of having a line of charge, we're just going to take that line of charge and wrap it into a circle. Okay? So now you can still think of it as sort of being a one-dimensional line of charge. It's just that one dimension is wrapped into a circle, all right? So if you want to, just imagine that this ring of charge has, well, a bunch of positive charges sort of all around here. And we're again going to say that it has a linear charge distribution, which is equal to Q over L. Or we could say that that is some tiny piece of it, which we'll call dQ over L. You can see that they've already chosen a little piece of the length there at the top, which contains some amount of charge and will contribute to the electric field over at some other point. We are going to focus on one specific point, which is point P that lies a distance x from the center of the circle, perpendicular to the plane of the circle. So we're only finding the total electric field at that one point, which in a way really kind of makes me feel sad, right? There's so much more that could be done there, but it's so much more work, and we have to do so much work just to get the equation for 1 point. So we're really limited by that, all right? It would take a whole lot more work to find the electric field at all the different points, which we're just not going to do, all right? So we're going to start by thinking about what's happening with the electric field at this point from all the little bits of charge around that circle. And once we do that, we can kind of see what symmetry's there and see what we need to focus on and see if anything cancels out, okay? So if this is positively charged at the top, we know over at point P, a positive charge would be directly repelled at that point. So that little piece of electric field points directly away from this top piece, all right? If we went to the bottom, you can imagine it's symmetrical. You get the exact same thing. There would be an electric field that's pointing directly up like this, just symmetric across the x-axis. Well, I could break either one of those into components, and you can imagine that both of them will have an x component pointing to the right, and both of them will have, we should really call it a perpendicular component. It happens to be in the y direction here, but there's one that cancels for both of those, all right? If I were to work my way around the circle and think about what this electric field vector does, you could imagine like maybe it starts here, but then sort of like draws its own circle. Can you see that? Perhaps, maybe. I didn't go high enough, though, all right? So it's starting below the x-axis, goes above the x-axis, and back around. Yeah? I see some nods. I see people who just aren't reacting at all. Are you alive? Okay, so work your way around the circle and think about what that little piece of electric field's doing. No matter where you go, there's always going to be a perpendicular component to cancel out the perpendicular component you're getting, okay? So all of these are going to cancel. Whoops. Will cancel out. And it's perpendicular to the x-axis. It might be in the z direction. It might be somewhere in between. Here they've drawn it in the y direction, all right? Every one of them, though, is going to give me this x component that we're going to have to consider. So what we're actually going to integrate is actually this thing, okay? So really this problem, in a sense, sort of works out the same way as the last one. As the last one, we had a y component that's canceling. Here it's a perpendicular component, and you always have something pointing to the right. That's all going to be added together, all right? So let's start with the equation. We could say that, well, let's do this. E total is going to be the integral of dE cosine theta, because we're only focusing on the x component. And we know that our equation for dE is dq, or k dq, over r squared. This one works out much simpler than the last one, okay? It's going to get to an answer much faster. So let's do a few different things here. Let me find my notes to make sure I'm actually looking at the right thing. We're going to start by rearranging this so that we have dq is equal to lambda dl. And we'll plug that in. So we'll let that be the first step. How are we doing with this color today? Good color? Should we use it the whole lecture? Yes? That was why? Is it purple? Okay, it's purple in your heart. I'll take it. Why not? So let's see. Now we have k lambda dl over r squared cosine theta. And there's an awful lot of constants in there, right? K is a constant. We know that. Lambda is some constant charge density, so that can come out. R squared is even a constant, right? This distance r is going to be the same no matter which part of the circle I'm talking about. So even the r squared can come out. And then theta, well, that's going to be a constant as well. No matter where I go in the circle, that angle is consistent. Well, that doesn't leave a whole lot to do, does it? So let's see. That's k lambda cosine theta over r squared times the integral dl. Well, that's just dumb. What is that going to come out to be? What is this thing? It's just L, so let's go ahead and write that first of all. So k lambda cosine theta L over r squared. And then let's see what we can do with some of this. What is this length in this particular case? It's 2 pi a. That's one way to look at it. It's just the circumference of the circle. Also, what is L times that? Q, right? If I take the density and multiply by the length, I just get Q. So we can rewrite this again. So let's see, we've got k, q, cosine theta over r squared. There's a couple more things I can do. Let's re-express cosine theta. Cosine theta, looking at the diagram, is x over r. So let's see, that's k, q, x over r cubed. let me see what terms I'd like to get this in. There's k, there's q, there's x. And then I'm going to re-express r cubed because I like it in terms of the actual distance away we are, x. So let's see, that's going to be k, q, x. And r is the square root of x squared plus a squared in this case. So let's put a little note to the side. R is x squared plus a squared to the 1/2. Which means this is going to be x squared plus a squared to the 3/2 power. Any issues in there anywhere before we discuss what it's telling us? Let me double check my work. K, Q, X, and then that stuff in the denominator. Looks good, okay? So in this case, everything worked out really nice because it was so symmetric, a lot was constant, and then one of our components also cancels out everywhere, okay? So the total electric field at this one point, a distance x away from the center, is given by that equation. But let's check sort of the extremes. What happens if x is equal to 0? Don't take too long. Somebody talk. What do you get for E total if x is equal to 0? Looks a whole lot like 0, right? So E total would be 0. Does that make sense? If I'm at the center of the circle, it seems like all the electric field should cancel out, right? For every one that's down, there's one that's up, and that happens all the way around. So that seems to be good. What if we go for x equal to infinity? Is it? Zero? You like 0? You sure about that? If x is really, really big, well, you could kind of think of that a couple of different ways, right? So if x is really big, then this is essentially gone. So I have x cubed in the denominator. We could write this as kq over x cubed, and you get something that looks like that, which is kq over x squared. Okay? If we're far enough away, but maybe not so far away that you can't even see the thing, okay? If we're really far away, it starts to look something like a point charge, okay? So maybe let's do something like this. How about x much, much, much bigger than a, but not infinity? Okay? If we're really far away, well, then that circle starts to shrink down from our perspective, and eventually just looks like a point charge Q. If you go even further away than that, eventually you completely lose its effect, and then essentially there's no electric field that's coming from it. Okay? Are we good? Sounds all right? Okay, so both of our answers seem to make some sense, so I think we got a good result there. All right? I have a whole extra slide here. Once again, what are we going to do with it? I don't know. Okay, I actually do have some stuff that I'd like to tell you, so let's do this before we draw the first number. Let's see. Distance, dependence, compared. Okay? If we have a point charge, we know that E is proportional to what? When we're talking about distance. Proportional to 1 over r squared, okay? So you can kind of imagine how the electric field drops off as I get farther and farther away from a point charge. We dealt with a long line of charge, and look back to Tuesday's notes. What was the dependence there? Was it 1 over r squared or something else? Essentially, if we talk about distance being x in that particular case, we could write that as just 1 over the distance r, okay? Which I think makes sense, right? If you have a line of charge instead of just a point, it makes sense that it wouldn't die off quite as fast. A 1 over r dependence makes more sense than just a 1 over r squared dependence. What if we had a plane of charge, which is a problem we haven't done? So instead of just a line, what if we spread that out across 2 dimensions? So we had a big surface, a big flat surface that was essentially infinite, let's say. This is a problem that might be in your homework. I know it's in the textbook. It's one we're not going to work in class, but you may see it elsewhere. It turns out that if I have a long plane of charge, there is no R dependence, which seems a little weird. I don't know that I have that equation in front of me. Actually, I do. The equation for an infinite plane is sigma, the surface charge density, over 2 epsilon, which means it's just a constant value of the electric field, which kind of defies explanation, but I'm going to try to explain it a little bit, okay? I think both of these others fit exactly what we would think. Like, as you get farther away from the charges, depending on what charges you have there, the electric field is going to fade away until eventually I get so far away that essentially I've got no electric field at all. However, if I have what might be considered an infinite plane of charge, or a plane of charge that's really, really big, if I'm a little bit away from it, that's the value of the electric field. If I'm farther away from it, that's the value of the electric field. If I'm really, really far away from it, that's the value of the electric field. Doesn't that seem odd? How is that even possible? Any thoughts? Yeah? Yeah, your explanation sounded exactly how confusing it is. Because it's hard. You're right. Yes, but it's hard to put into words. I'm not even sure how to put it into words. Yeah, you want to add to it? Those words are correct, and these words are correct. And can we add to it some more? The plane is all in one direction, but it's still composed of, individual charges in there that have electric fields that are spreading in all directions. And then those components all add together to give you something that's essentially pointing straight away from the plane. But again, why no dependence on distance? If one way to think about it, you're both correct. You're all correct, actually, in a way. If you imagined floating, I should just stop there, shouldn't I? That sounds like fun. Imagine yourself floating above a surface that's perfectly blue and has no structure, no anything. You just look down, you're like, it's blue. And you look as far as you can in all directions, and you see a blue surface, right? Can you really tell how far away from that surface you are? Because if you get a little farther away, you're still like blue as far as the eye can see. If I get closer, it's blue as far as the eye can see. There's no structure to tell me I'm closer, farther away, or anything. It's just blue as far as the eye can see. That's essentially what's happening here. If I get farther away, well, it's almost like the edges sort of come in and have an effect now because of my greater distance. If I go farther away, there's always more of infinity to still come in from the edges and have an impact on me. I'm pretty sure that's what we're all trying to say, just in different words, okay? So for an infinite plane, we essentially just have a constant value for the electric field. I would suggest either looking in the book or looking in your homework and work through that problem. It's not terribly different than what we did on these two, okay? But it's good practice. So what are we going to do next? I think we need to find a number. So I have a thing here. Ooh, look at this. That's not our number. Instead, we're going to get it to pick our number. Go. Is there another one? Oh, are there more? There we go. It decided on 54. Wait a minute. You've got 54? And you've got 54? I'm confused. No? Ooh. You got a 54? No 54. You've got a 54, like in your hand there. Okay. So do you want to ask a physics-related question, ask me a question, or defer to one of your neighbors? Oh, a personal question. Do I like bagels with cream cheese? How much cream cheese? No. A little bit of cream cheese, that's good. But if you go like somewhere where it's just like there's just cream cheese like oozing out the sides, no. The point is the bagel. No? Who says cream cheese? Lots of cream cheese. Who says no cream cheese? Oh, just plain bagel. Or something else. What's that? Yes? Who says no bagel at all? Like eat something else. How about a biscuit? You know, like a biscuit from, you know, it's like all fluffy, you know, biscuit. A biscuit's where it's really at, but that's a good question. I like that. Did you think of that in advance or did just, no? Okay. Let's go a little further. I'm curious what the next question is going to be. Oh, you have an add-on? Okay. So we're going to increase the dimensions into potentially other dimensions than the ones we're aware of. Good question. I want to say yes, but I can't say that 100% for sure because I don't know off the top of my head. It would make sense, but I'll let you look it up. His question was better. Like bagels and cream cheese, that's a better question, you know. I'm sorry. So let's see. What do we have going on here? There's not a whole lot to talk about here because we've really been doing this all along. The concept of electric field lines. Electric field lines are kind of how we typically draw the electric field because it's kind of no fun and difficult to like individually draw all the vectors, right? Like it's going to get messy really fast because I need long vectors close, and then as I get farther away, I need shorter and shorter vectors, but I need a vector at every single point. So I can't really draw that. Either I have to choose a set of vectors, or what if we just like connect all of the vectors that are leading away and understand that that gives me the direction at every point, but really tells me nothing about magnitude. I have to keep in mind that as I go farther and farther out this line, that actually the electric field magnitude is dropping, okay? This is handy, though, because it gives us a way to sort of visualize the electric field everywhere without having to worry about all the individual vectors, simply by playing connect the dots a little bit, okay? Just connect all the vectors that are leading away and sort of see what that looks like. So you can see for the positive charge, as expected, well, the electric field lines lead away. Negative charge, they point in. I want to point this out to tell you sort of the conventions that are used when you're looking at electric field line diagrams. You'll notice two things, and really they're kind of the same thing, just told in a different way. The number of lines at a charge, in other words, starting from the charge or terminating at the charge, is drawn compared to other charges such that it's proportional to the charge magnitude. So you'll notice we have Q and 2Q. There should be twice as many lines that are going into this charge as there are there. I'll trust that's true without counting them. Someone is already doing it. Is it double? 8 and 16, I think. Yeah, that's good, okay? So if we had a 3Q, we should have 3 times as many lines going in to give us a feel just at a glance at how strong that charge is. That ties into this idea that if I want to look at the field strength at any point in space, well, it's related to how dense the lines are at that point. So if I were to just say pick, this little region out here, and look at how many lines are sort of passing through that area roughly, of which, well, the way I've drawn it, there are none. Just keep in mind, there are more. We just draw some of them. Compared to, say, a similar region over here, well, there's a higher density of field lines over there than there is over here, which indicates twice as much field strength, okay? So we could take that a little further and look at more complicated situations and how the field lines look, or we could go back over here and play with this little thing again, where there were the vectors we had before. Again, the colors are trying to give you some feel for the strength, and also as they fade out, it's giving you a feel for the strength. If we just switch that over to field lines, whoa, things are just a little cleaner, okay? So you can just look at those and get a feel for what the electric field looks like at any point. Configuration A and configuration B, oh wow, it even changed again and gave us arrows. I wonder what the two configurations are. I truly have no idea. It's just more charges. Ooh, that one's creepy. Can I move these? Ooh, we can. Ooh. All right, we'll let that play around for a second. It's going to draw some vectors here in a second, too. Come on. It's still drawing red lines. There we go. Now we can see which way they're pointing based on whether they're positive or negative charges, all right? That's kind of all you need to take away from field lines, just the fact that you can look at them and kind of deduce what's happening, all right? So let's go back over here.
Castrate the castrators, snip, snip, crush with stone. Thou shalt not destroy the planet. Commandment 11. If you don't like it, dig a hole, and I'll send you a flower.
Just making sure everything's okay. It went in the next door classroom as well. But now seems to be leaving. Thoughts? Was a nice dog. Yeah, very nice dog. I will say this. If anyone returns, someone call security, since I really can't in front of the room at the moment, all right? Just someone. Take it upon yourself. I don't know what the number is. It's online. I can't remember. Yeah, just have it ready because I don't want us to end up in a dangerous situation. Everything's okay now, though. Let's see. I think we need another question. After that, agreed? Yeah, okay. So let's go back over here and pick another number. This needs sound. Oh. No one's got 27? You do? If you don't like having 27, you can immediately defer. Do I pick the homework questions? We take turns. There are some questions that have been chosen at points in the past, and we take turns, me and the other professor, looking through those each week and deciding whether we feel they're appropriate for the semester or not, and go from there. So if you're wondering if I did which week, I don't remember at this point. I did last week, maybe? I can't remember. Bad homework? Bad, evil, dark homework? Okay. Sorry. Wait a minute. Another question. A cheat sheet. You are going to get the equation sheet that's been posted on B courses already, and that's all. Okay? So the equation sheet that's there, the idea is it was actually put together after the exam was, so we're sure that everything you need is there. But of course, there's more that's there. Otherwise, we'd tell you which problems you're being asked. So the problems and what you need will be given to you. You don't have to stress about memorizing stuff. You have more questions? You want to just keep going? No? Okay. All right. Well, then let's head back over here and carry on. I'm going to not say a whole lot about this right now. In the next chapter, 2 chapters from now, we're going to come back to this thing known as a capacitor, and we're going to learn about it in detail. We're going to use the electric field it creates specifically 2 chapters from now to be able to do some specific problems. It turns out that if I take 2 conductors in this configuration, and don't imagine these as just lines of charge, they're actually planes. So if you think of, you want me to try to draw it? That's not, like there's a plane here somewhere. Yeah, and it's got positive charges all over it. You get the idea, okay? That's perpendicular to the screen. And there's a negative one. If those are really large compared to the distance between them, it turns out you get this uniform electric field that directly points from the positive to the negative, and it's also constant inside there, okay? And again, we're assuming that maybe this goes on for quite a while in both directions, and we're nowhere near the edges, and we're somewhere sort of in the middle of this. It turns out that this constant electric field is really handy for calculating some other things because it's basically the most simple electric field that we can create. Just a constant one where we know exactly which direction it's pointing. We can do experiments, and there's a lot of problems we can work based on this setup, okay? Yes? Yes and yes. So, for instance, take a look at this. If I were to just flip that on its side, and believe it or not, I wanted to just go like this and expected it to change on the screen, but that's not going to happen because I have everything locked. So, if you imagine that charge is being dropped in between those plates, kind of, okay, and it will move according to the forces that are on it. We're going to do some problems based on that one example at least, and there may be some in the homework as well, okay? So you are correct, but we'll get to that in a little bit. So let me ask you guys these questions. Look, the answers are there. Why are they there? They shouldn't be there. Looks like the one on the left is negative, and the one on the right is positive, so let's just skip right over that. But you'll notice the field lines. There are 6 for the left one, and there should be more than that over at the right. I don't know if there's enough. Should be twice as many. They haven't drawn them all, I don't think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 12. Wow. At first glance, it didn't look like there were 12. How about this? Just ignore the answers that are covered up by the weird sideways glance smiley face down there. Yeah, I don't know why. Which one has the greater magnitude? Well, you can just look at the last slide, and it will tell you. I don't know what happened with the copy and paste there. Just ignore it, okay? So, next topic we need to talk about will lead us a little bit into the next 2 chapters, and that is how electric fields and conductors interact with each other, okay? How do electric fields and conductors interact? There are 3 things that are going to happen, and these are all kind of based on the same concept that we talked about when we were talking about conductors to begin with. Just the idea that in a conductor, the electrons are basically free to move around, okay? If I give them a force and give them a reason to move, they will move, okay? So if I start with the first one and I have any net charge on a conducting material, well, you can imagine that extra charge is going to repel the other charge and try to get away if it can. The place it can go to get away as much as possible is all the way to the outside surfaces, okay? And this happens because, again, charge is free to move. So you can imagine if we had something, we just like dropped 2 extra electrons on the conductor, they're going to run as far apart as they can all the way to the edges. So any excess charge, any net charge, distributes itself on the exterior surface of a conductor, not of an insulator. With an insulator, I can sort of put charge wherever I want to because the charge I put there stays where I put it because it's sort of locked in place, all right? Because of the first one, the second one happens, and that is that the electric field inside the conducting material itself is going to be 0. In the material of the conductor, the electric field is 0. Take a look at this diagram on the top right. And this is sort of after everything has settled out and all is done. So imagine maybe we started with a conductor that was neutral. It has no net charge at all. And then I decide to drop this positive charge sort of in the middle of that conductor. Maybe it's a ring. Maybe it's actually representing a sphere. Either way, the same idea, okay? Well, since charges are free to move around, you can imagine that electrons are going to run toward that positive charge, okay? and try to sort of go as far as they can in an effort to kind of cancel out its effect, which leaves me with a net positive side and a net negative side of that conducting surface. Okay? You can imagine when that happens, we get another electric field that's created in the direction of the arrows that I've shown there, pointing from those positive to negative charges. So what's happening is this electric field coming from this center charge, well, it's attempting to pass all the way through, and in a way it does, except this separation of charge creates another electric field in the opposite direction, such that within the material itself, it cancels out, okay? So I get an electric field in here, and we get an electric field out there, but because of charge motion in the conductor, you get net zero electric field in the material, okay? Are you okay with that idea? That's kind of all right, okay? So what happens with the third case? The third case, the electric field will always be perpendicular to the outer surface of the conductor. The electric field is perpendicular to the outer surface, and I think, at least they drew it that way in the top right. It looks like that's true, perpendicular to the outer surface, okay? And this diagram in the middle at the bottom sort of shows us why. And it goes back to the idea that the charges are free to move around. So here we have a case where the electric field is not perpendicular to illustrate the fact that it has to be. So if you imagine trying to have an electric field that's off at some angle, well, that immediately gives me a perpendicular component and a sideways component. And if I have a component that's going to the side, well, the charges are free to move in that direction. They feel that force, which means charges are just sort of going to shift in such a way until everything is balanced out again, and then I end up with an electric field that points straight up. So it's like if I try to make it not be perpendicular, charges just move such that they repel each other equally, and you end up again with a perpendicular electric field. Okay? So these second two are really all based on this top one, okay, and the fact that they can move around. Any questions or thoughts about any of that? Yes? In the material, it's because charges move and separate so that I have net positive on the exterior surface and net negative on the interior, and electric fields point from positive charges and toward negative charges. So you're going to end up with exactly that situation sort of all the way around, and it's just enough to cancel out what's passing through in the other direction. Who else? Yes? Anytime it says the charge is spread throughout, like a volume, the only way that's going to happen is if it's an insulating material. If it's a conductor, it has to be on the surface. The problem should give you enough information to be able to tell between if it doesn't just explicitly say. Yes? You're asking about an extreme case. I can't imagine that happening. No, I can't imagine it happening. Anybody else? Things do get struck by lightning and break. I would agree with that. Yes. Was there a question there somewhere? I mean, I guess everything has its limits in a way, but just dropping a regular charge in there that's really large, it should be able to cancel out. What's on the next slide? It's this problem. We should probably work this problem. Actually, let's go ahead and do this. Why not? Okay. So in this particular case, we've got a charge particle that is an electron. It's given a velocity directly to the right, and it enters a uniform electric field that's between these parallel plates. We're going to assume the field is, it says uniform and downward, and that the field outside is essentially zero. The electron is also entering about halfway in between the plates. So you can see it's got a half a centimeter above and below. We are going to try to find what? Where is this question? Here we go. If the electron, we'll say, barely misses the top plate as it exits, what is the value of the electric field? The electron barely misses the top plate as it exits, kind of as it's drawn there, at least roughly. What is the value of the electric field? We are going to assume in this problem that the only force at play is the electric force. So if you're thinking like, ooh, what about gravity? I don't know. Maybe this whole setup is happening somewhere out in deep space and there's not really any effective gravity nearby. Only the electric field is at play that's affecting the motion of the charged particle. So we could say, first of all, that the force on the electron is equal to Q times the electric field. And we know that Q is just the elementary charge. So if we can find something about the force, then we can find something about the electric field. So we could rearrange that and just say that E is equal to F over Q. And since this is the only force, we can say that the mass of the electron times its acceleration is equal to that force. Only Fe, we'll say, at play. And in the denominator, we'll just write E for the charge. So how can we find the acceleration of the electron? Any thoughts? That's helpful. I would agree with that. I don't know who said that. Somewhere over here somewhere. Yeah, there you go. Okay. So we know that it has to travel this far, 2 centimeters, in the exact same amount of time that it goes this direction, a half a centimeter. Okay. You could think of this as basically a projectile problem. It's just instead of gravity that's bending it in one direction, we have an electric field that's bending it upwards instead of gravity bending it downwards. Okay? So in other words, we have a constant velocity in the x direction. And we know that that velocity in the x direction is 1.5 times 10 to the 6 meters per second. And we have a constant acceleration in the y direction. And that acceleration is what's coming from the electric field. So what we can do, first of all, is find out how much time is required for it to get from the left to the right. So we could say that the time is the change in the x position divided by the velocity in the x direction. So that's 2 centimeters, 0.02 divided by 1.5 times 10 to the 6. So that happens really fast. I've got 1.33 times 10 to the minus 8 seconds. It's moving. Electron, so little mass. We can make it go fast. Rhymed. Now I'm kind of sad about myself. So in the y direction, we can do a similar thing and use one of our kinematic equations, which looks something like this. I'm sure you've seen it, although maybe it was written a little bit differently because it seems like everyone wants to write it with different subscripts and make it look slightly different. So y final is going to be a half of a centimeter. We could say that y initial is 0 and that v initial is 0. And you can solve this for the acceleration. And you should get an acceleration of something here that I can't quite see. Oh, I don't know what that number is. Let's try 5.65 times 10 to the 13th meters per second squared, which we can plug back in over there. Which, if we pull everything together, gives us 322 newtons per coulomb as the value of that electric field, based on its projectile motion upwards. Okay? So when I have charged particles, it gives me control over the motion of things in a way that gravity doesn't. We don't really have any control over gravity, right? It's just like, oh, we've got some mass that's nearby, like the Earth. Well, I can launch things in a direction, and it's going to cause the acceleration it's going to cause. But if I have a charged particle, like I can create electric fields, and I can make that electric field have any orientation I want, because I could take these two parallel plates and tilt it on its side, put it at some weird angle, and then by varying the electric field, we can control how much it bends to one side, and we can make that electron sort of go wherever we want, which may be something that you're thinking about a little bit. Was that you that brought it up a second ago, or you? Who was it? It was one of you guys. Someone over there talked about electric fields and magnetic fields and bending projectiles, these things. Okay, that was you. If you think back to old televisions, like old televisions, you know televisions? You know, these televisions, right? Have what's known as a cathode ray tube inside, which is basically something that can shoot charged particles. Well, the way that it drew a picture was by taking charged particles and making them curve and follow a certain path and hit the front of the screen in exactly the right spot. And there was a material there that when hit with a charge would glow. Well, first of all, that sounds difficult, right? Because what you need to do to draw a picture is then essentially get an electron to like go and hit somewhere and light that up, and then go to the next point right nearby and maybe light that up, or maybe not, depending on like exactly what you're trying to create. And then do that for every little place on the screen. And then you need it to do the whole screen fast enough so that you can actually see video, which means it needs to do the whole screen at least about 30 times each second, which all of a sudden makes old television sound like a miracle in a way, right? Using a technology kind of roughly like this to make the electrons go and hit the screen where you want and do the whole thing that many times each second seems miraculous, okay? But that's basically the idea, controlling charged particles and making them go and do what we want to. Well, that makes us sound powerful all of a sudden. I think I'm ready to ask you guys another question. Let's hop back over here. I can sense the nervousness. Ooh, it does have sound now. Oh. 8 it is. Did anybody get 8? Because they're not quite all gone up here. 8. Physics, personal, or one of these two people?
Okay, yeah, so I got a suggestion.
A suggestion?
Yeah, personal question about who's your wife.
Who is my wife? And?
Yeah.
Was there a follow-up to that? Like
Personality, okay.
personality. Well, these are a lot of questions all of a sudden. Interpersonal dynamic. What is she quiet because I'm loud? Make this louder. Her name is Caitlin, and she currently has the flu. What's that? I don't need to tell you that much. And she's a medical doctor, and she has the flu. So you know who's getting the flu next? Yeah, we both had our flu shots, but alas, what's going to happen? I don't know what else to add to that question. I could say all kinds of things about her, but I don't know how much you really need to know. Is she quiet? No. I'm the quiet one. Mm-hmm. Yeah. If you looked at the two of us, you would think I was an introvert and she was not. But actually, we are both extreme introverts, believe it or not. Yeah. Let's do another one. And then we're going to talk about dipoles. And then we're going to be done with this chapter. 46. No 46? Must be up front here. Or no one wants to admit to 46. Or you're checking all your numbers. This is not bingo. You know? Got a whole playing card over there. Okay, nobody got 46? Too bad. I guess we go back to this. All right, so we answered that question. Let's see, did I skip anything here? I feel like I skipped something. No, I didn't. We actually talked about all that? We did. Okay. So we've got dipoles to talk about. Why talk about dipoles? Dipoles are simply two charges of the same value of opposite sign that happen to be near each other. So you can see the basic idea illustrated there at the top, where I have a negative Q and a positive Q. They're separated by a distance L. And you'll notice the addition of one additional piece of information there, which is known as the dipole moment vector. You can see this thing P. Ooh, the dipole moment vector. By definition, it points, we'll say first of all, from negative to positive, and it is equal to Q, which is just the magnitude of either one of the charges since they have to be equal, times L, the distance between them. And if you're wondering why bother with this particular configuration of charges, it's because it kind of happens a lot, especially in nature. In this particular case, we have a water molecule, which could be modeled this way, which is consisting of two different dipole moment vectors, pointing from negative to positive, and then you could add those two together and get a dipole moment vector that sort of points directly to the right. This happens essentially in any polar molecule because you have a positive and negative side, and you have a separation of charges that remains relatively consistent. If I put things like this in an electric field, stuff happens, as we'll see. Yes? It's you could just say it's the magnitude of Q. They're going to be the same, so it's just whatever one of them has. Okay? Yeah. 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 Well, the thing, you're dealing with, I mean, there's an electric field there, but it's also spread out a lot. You know, so how, I would say that that's something you could look up and see if there's anything significant, but you're dealing with such a large area, and also even depth as well, and each individual molecule is not going to have a strong electric field. So I would suspect it's probably negligible but measurable. Good question. Okay. So let's see. What should we add to this? Is that all that we need to put on that slide? Yes. What happens if we take something that has an electric dipole and put it in a uniform electric field? We can see this example down here to the right. So we're ignoring the electric field being created by the dipole itself. We know that those charges are going to create electric fields. There's additional complexity there that we don't really want to look at. We're going to assume that its electric field is very small in comparison to the electric field that we're putting it in, that's pointing directly to the right and is being created by something else. So maybe there are two parallel plates in a capacitor that are generating a really strong electric field, and we just drop an individual water molecule inside that has a dipole moment, okay, if you want to think about it that way. So take a look at what happens. We'll notice that the positive charge at the top, well, it feels a force directly to the right. The negative charge feels a force directly to the left, and since Q and E are the same, well, those should be identical forces. So in other words, we can say that the net force on this is going to be equal to 0. So the electric field isn't going to try to make the entire dipole move somewhere because there's no net force. So it's going to stay in its position, but you'll notice that, well, if you imagine that it has an axis in the middle, this is going to create a net torque. As we've described it here, it's going to try to rotate the dipole clockwise, okay? So we could add to this the net torque is not equal to 0. And that's a value we can actually calculate. So if I wanted to find the magnitude of the torque in this particular situation, does anybody remember anything about torque from last semester? Did you enjoy torque? You did? Students typically don't. You like torque? Who's a torque fan? A little bit. Like, who? What a weird thing to ask, right? Like you're going to wear a shirt. Torque. You know, like, I don't know. There should be a band named Torque. Is there? No? Yes? Maybe? I'm starting one. It'll be terrible. Torque. kind of band would it be? Maybe like a classical quartet. No, I don't know. I don't know what's happening anymore. So we can calculate the torque here. It's going to be equal to F sine theta times L over 2, if L is the distance between those two molecules and the axis of rotation is right in the middle, plus, well, another one of those because we have another one coming from the other molecule as well. Remember, it's the tangential component of the force times the distance to the axis, or you can think of it as the force times the moment arm, which is a perpendicular distance over to the axis. Either way is perfectly fine. Let's see. So we can rewrite this. We know the force is coming from the electric field, so both of these is going to be Q times E, so QE sine theta L over 2, plus QE sine theta L over 2. And then you'll notice we can add those together because they're exactly the same, but also both of them have this term in it, Q times L, which we learned on the last slide is actually the dipole moment vector P. So we can rewrite this as, let's see, PE sine theta over 2 plus PE sine theta over 2, which of course is just going to be PE sine theta. You might recognize that, okay? P is a vector. We're just looking at magnitudes here so far. E is a vector. And sine of theta, that's the sine of the angle between those. That's actually a cross product. So we could take that and say that the torque vector on the dipole is the dipole moment vector crossed with the electric field, which is kind of nice after working through that. You appreciated that? Yeah, you liked that? Okay, yeah. Mm-hmm. Nobody else did. Look at them all. So sad. Yeah. Oh, high fives. Yeah, okay, you both liked it. That's great. So we end up with a cross product that's hiding in there. So what is this thing going to do? Take a look at the forces causing this torque. If I drop the dipole in so that the dipole moment vector is perpendicular to the electric field, the torque is going to rotate it clockwise and essentially bring it to rest at some point. There might be some carryover momentum, but then the torque would reverse, and eventually this thing should settle out so that it's parallel to the electric field, okay? So the overall effect of this is to try to rotate the dipole so that it's parallel to the electric field. You might imagine that if it's doing that, it's going to do some work. And to bring up something else from last semester, if I'm dealing with the work done by a torque, it is the integral of the torque d theta as it moves from some theta 1 to theta 2. And then we're going to plug that in for the torque. And let's see. Keep in mind that typically when dealing with torque, we say that counterclockwise is the positive direction and clockwise is the negative direction. That's the typical standard. So this is actually considered negative rotation or negative torque. So in other words, we're going to plug in negative PE sine theta, d theta from theta 1 to theta 2, which you can integrate, and you're going to get another negative sign out of that and end up with PE times cosine theta 2 minus cosine theta 1. This is the work done by the electric field as it rotates the dipole. So you might imagine that, well, as the electric field does this positive work, it is decreasing the potential energy for the dipole. It's almost like it was a spring that had been pulled back or stretched and then released, and it wants to get back to equilibrium. If I have a dipole that's perpendicular to an electric field, that is not a state of equilibrium. Its equilibrium position is actually being parallel to the electric field. So when it's perpendicular, it actually has some potential energy that it loses as it rotates into the parallel arrangement. Okay? Does that make some sense? A little bit, perhaps? No? Yes? All right? So this is not equilibrium. And we could say that parallel is equilibrium. Okay? Ooh, how many more slides do we have here? Do I have enough room on this one to squeeze in what I want? So here's what we want to do, and this is actually going somewhere to help us find how much potential energy a dipole has. So let's do a couple of different things. First of all, remember that the change in potential energy is equal to negative the amount of work done. That's just in general. For any type of work done by any force and its associated potential energy. And for this particular case, we need to pick a place where the potential energy is going to be zero. And keep in mind, even though it may be a little bit counterintuitive, we can pick that position to be anywhere. Like when we're dealing with gravitational potential energy, it might be natural to say, ooh, let's let the floor in here be the location of zero gravitational potential energy. But I could just as easily say, hey, let's let the ceiling be zero, and let's say that these are negative potential energies as for objects in the room. Doesn't really matter, because when we calculate a change in potential energy from one place to another, you still get the same value no matter where you say zero is. So for this particular problem, we're going to let zero potential energy be at the location when the dipole moment vector is perpendicular to the electric field. So when it's vertical in this direction, we're going to say that is our 0 point, when u is equal to 0. And we're only doing that for simplicity's sake with the equation that comes out of this. So in other words, we are going to say that theta 1 is 90 degrees, and that'll mean theta 2 is just going to be what we call theta in this particular case. So theta is just how much it's rotated away from the vertical direction. And let's take those and put those into the equation just above. So we could say that work is equal to PE cosine theta minus cosine 90, and that is just going to give me, well, 0. So I get PE cosine theta for the work. And since u is equal to negative the work, we can say that that's equal to negative PE cosine theta, which should make you happy again. Because PE cosine theta is what? That's a dot product. So the potential energy stored by a dipole is negative the P vector dotted with the electric field vector. So we've got three different things there. We've got torque caused by the electric field on the dipole. We've got the amount of work that's being done by the electric field on the dipole, and we've got an equation for the potential energy being stored by the dipole when it's in some orientation. Okay? Who's got questions before we move to the final slide of this chapter? Yes. Connecting it back to, so E internal is equal.
When you pull this is the first time we've used stencil and work in like this class.
Yeah.
That's why I'm connecting it back to it.
Yeah, that's true. Yeah, everything you said there is true as far as I can think of.
So in a more complex system, what there is like practical, like you could just do that.
Yeah. Often when we're working problems like this or others, we're trying to isolate it just to learn the concept and sort of ignoring the other effects. Yeah.
Did you say that also, like, so all the three things that we had over there, like the torque, the cost, and dot product, and potential energy, you said W, the work is just dot product without the negative sign?
Dot product, but without the negative sign.
Work is just P cosine theta?
Basically, yeah. Yeah, because, I mean, work and energy have the same units. One is essentially just the negative of the other. So, yeah. Anybody else? Final slide, okay? But before we do that, of course, I want one more. I'm just curious. 38. You already asked a question. Okay, go. Okay. I understand. Midterm is only thermodynamics. So all of this stuff you've been listening to for the last couple of classes, you didn't really need to yet. Right? So I hope that you... What is happening? Bitdefender box? I don't want Bitdefender box. Where was that ad I clicked on? There it is at the bottom. Look at that. For all your internet-connected devices. We need Bitdefender box for this door is what we need. Because, yes. I think so. Check the syllabus, but I'm pretty sure it is. Yeah. Okay? So, last thing is sort of flipping this thing around and actually talking about the electric field that is being produced by the dipole. We assumed it was negligible in the last slide, so we could see the effect of an external electric field on it. But we can quickly sort of work out what the electric field looks like, at least at one point, once again. Okay? So you'll notice we have a negative charge bottom left, positive charge bottom right. We are looking for the electric field at the point P, which is halfway in between the two and some distance perpendicular away. So you could say that that point P is on the perpendicular bisector of the dipole. All right? We're only finding the electric field at this point. So for starters, imagine what's happening because of these 2 point charges. So because this is negative, if I imagine a positive test charge here, that creates an electric field toward the negative charge. And because this one is positive, this is generating an electric field that would be repulsive that direction. Again, because these are equal, well, the y components should cancel out, but both of them have a left component that adds together. Okay? So let's write that down first of all. We could say that the y components of the electric field cancel, and we could say they both have a negative x component. All right? So what we could do is just perhaps, let's write this as E from the plus charge and E from the negative charge. These are going to be equal to each other. And both of those are equal to KQ over R squared, but they've drawn a weird R here, which I think is just confusing. What we're actually looking for, of course, are these two hypotenuse. What's the plural of hypotenuse? Hypotenuse? Hypoteni? Hypotenuses. No, I don't know. None of it sounds good. I don't know what's happening. So looking at that diagram, this is going to be R squared plus L squared over 4. Okay, so we're squaring both of the sides of the triangle that's there. And again, because the y components cancel out, we could say that E total is just going to be 2 of these. So let's write it as 2 times E plus, or minus, since they're the exact same thing, times the cosine of the angle to just get the x component. And they've labeled this angle as phi. So let's plug that in and see where it gets us. So we've got 2 times KQ over R squared plus L squared over 4 times the cosine of phi. And you'll remember that K is actually 1 over 4 pi epsilon naught, so I'm going to use that to get rid of the 2, which brings me to 1 over 2 pi epsilon naught, again because of what we have there for K, times Q over R squared plus L squared over 4. And then I want to do something with this cosine of phi. So looking at that, that's going to be the adjacent side over the hypotenuse. So I could rewrite that in terms of R and L as, let's see, L over 2 over R squared plus L squared over 4 to the 1/2 power. Okay, so we're just using adjacent over hypotenuse in the diagram there above. And then we can combine a few things. Okay, so I've got that extra 2 that's hiding in the denominator of the numerator, if you want to think about it that way. Let's bring that down. So we've got 1 over 4 pi epsilon naught. And then I have Q times L in the numerator, and we know what that is. And then we've got a couple of these things in the denominator, which is going to give me R squared plus L squared over 4 to the 3/2 power. And then, of course, we can combine the Q and the L, so that's just P. And then we also have a K that's sitting out front, and all that is over R squared plus L over 2 to the 4, and that's to the 3/2 power. So we use the exact same approach for point charges. We just have 2 point charges here. It doesn't come out terribly pretty in the end by any stretch of the imagination, but it just shows you a little bit more we can do to find the creation of the electric field by 2 point charges, where maybe we don't have any values. I need to add one thing to this, and then we are done for the day. What if R is much, much bigger than L? What does this equation look like as R is bigger than L? Looks like we're going to get K times P over R cubed. Does that make sense? Why R cubed instead of R squared? Or R? So it's falling off faster than a point charge by itself. Yeah, because you've got 2 opposite charges there, right? As I get farther and farther away, like you can imagine, they have some canceling effect because one is positive and one's negative, so that the electric field is disappearing faster as I increase the distance away, all right? That is all that we want to say about this chapter. Yay, we finished another chapter, our first one in electricity and magnetism. Go us! Go team has been said. Yes, go team. Get out of here.